GCE Advanced Level Chemistry Practical Series, Experiment number 4, Preparation of Standard Solutions. So students, let's take a look at the aim of this experiment. So the aims are listed down here. The aims of this experiment is to gain skill of using glassware and 4-beam balance. That is one of the aims here. To develop the skill of measuring volumes and to gain the competency to prepare solutions of required concentrations. So there are three main aims to this particular experiment. We are going to learn how to use triple beam balance. We will be learning how to measure volumes accurately. And finally, I will be learning how to prepare standard solutions. There are solutions that are known as standard solutions, and we are going to learn how to prepare these standard solutions. Introduction. Methods of determining the composition of a solution is the main task that we will be looking at today. So when it comes to talking about measuring the composition of a solution, there are few ways in which we can measure the composition, or we can talk about the composition of a solution. One thing is by taking the percentage composition of a solution. So there are few methods we can obtain the percentage composition of a solution. We can take a look at the mass percentage of that particular solution, or we can take a look at the volume percentage, or finally we have percentage of moles that speak about the composition of a given solution. So let's take a look at the first one. Percentage of mass, or mass percentage, is calculated by taking mass of the solute divided by mass of the solution and then multiplied by 100. So for example, if a question says that you have a solution that has a total mass of, let's say, 100 grams, and now this is the mass of the entire solution. And imagine in this solution we have let's say 5 grams of sodium chloride. Inside this 100-gram solution, let's say there is 5 grams of sodium chloride. So what will be its mass percentage, or percentage of mass? So to calculate that, to calculate the percentage of mass, we will take the mass of the solute divided by mass of the solution. Keep in mind you have to take the mass of the entire solution here, and then you multiply this by 100. Now, as I said earlier, the mass of the solute was 5 grams, and the mass of the entire solution was 100 grams. Then you have to multiply this by 100. So the final answer would be 5%. You can see grams cancel off, 100 cancel off, leaving off just 5% as the answer. So when you're calculating the composition of a solution as a mass percentage, you will have to follow this particular method, and the equation for that is given here. Mass of the solute divided by the mass of the solution. some of you might still not know what solution, solvent, and solute means. So let's have a look at that. When it comes to a solution is made by mixing a solute and a solvent together. Solute is usually the minor component of a solution, and solvent is the major component of a solution. So solvent is going to be seen in a larger amount, and solute is going to be seen in a smaller quantity or smaller amount. So if you take 5 grams of NaCl and add it to 95 grams of water, right? So this is your solute in a smaller amount or smaller mass, and you have your solvent. What we are dissolving the solute in usually is the solvent. And when we dissolve both of them together, we produce a solution. We can say NaCl solution. Now we added solute plus solvent. The result is a solution. We took 5 grams of the solute, 95 grams of solvent, which is water, and the solution has a mass of 100. This is how we would normally learn about solvent, solution, and solute. You can see when solute and solvent is mixed together, what we form is known as a solution. You have to be very clear when you're calculating the mass percentage. The solute mass is going to be divided by solution mass, not the solvent mass. It has to be divided by solution mass. Keep that in mind, students, very important. And now we will move on to the next part. Now we are taking a look at percentage of volume or volume percentage. Certain solutions can be made by mixing two different volumes together. For example, if you take 15 milliliters of ethanol and dissolve it in 85 milliliters of water, you can actually produce 100 milliliter solution. So when it comes to their percentage, you can easily calculate that by using this formula. Volume percentage is equal to volume of the solute divided by volume of the solution. So if you take this as an example, if you have a solution that is made with 15 milliliters of ethanol. If you make a solution using 15 milliliters of ethanol and 85 milliliters of water, right? When you add them together, you actually produce 100 milliliter solution of ethanol, a solution of ethanol. So what is the overall volume of the solution? 100 milliliters. So what is the composition of this particular solution? We can talk about the composition of the solution by talking about how much of ethanol is spread throughout this 100 milliliter solution. the entire volume of the solution is 100 milliliters. In this 100 milliliter solution, how much of ethanol is spread out or dispersed or dissolved in this 100 milliliters of the solution. So in this 100 milliliter solution, we have 15 milliliters of ethanol dissolved in it. So we can easily talk about the composition by taking that into account. We can say the volume of the solute is 15 milliliters and divide by the volume of the solution, which happens to be 100 milliliters. So 15 divided by 100 multiplied by 100 over here results in altogether 15%. So volume percentage is going to be 15% when it comes to the example that we took here. So that is how you normally find the concentration or not the concentration, that's how you normally find the composition of a solution if we are going to be talking about the composition of the solution using volumes. We can talk about composition of solution using moles as well. This is another example. So we can talk about the composition using percentage of moles. So again, a solution is made with solute and solvent together. So we need to talk about, out of the total number of moles, how many moles of the solute is there. So if you take a situation like this, imagine we have calculated that there is 1 mole of some substance, let's say sodium chloride for this matter, and there are, let's say, we'll take 10 moles here, right? 10 moles of sodium chloride and over here 990 moles of water. This is just an arbitrary example so that you develop an idea about what or how we can actually measure the composition using moles. So if you have 10 moles of sodium chloride dissolved in 990 moles of water, that can be used to calculate the mole percentage. Mole percentage can be calculated by taking the number of moles of solute divided by total number of moles. Which would mean we have to take number of moles and then this has to be multiplied by 100. Don't forget that. So 10 moles is the number of moles of the solute divided by total number of moles. Total number of moles mean you have to take into account both the solvent moles and solute moles. Solvent and solute moles together is what is going to be the total number of moles in solution. So when you solve this, you're going to have 10 moles here divided by 1000 moles multiplied by 100, resulting in 1%. You can see 2 zeros get cancelled off here, 200, and 1 zero get cancelled off here. Moles cancels off. So the final answer is 1%. So this is how we can actually use a mole percentage to talk about the composition of a solution. So these are few ways in which we can talk about the composition of a solution using percentage. Using percentage, we can talk about the composition of a solution in this manner. Now, just a second ago, we learned about a few different ways that we can use to talk about the composition of a solution. Mass percent, percentage by mass, percentage by volume, and percentage by number of moles are the few different ways we spoke a little while ago. Out of these few ways, we use mass percent or percentage by mass quite a lot. So we use this particular formula as we saw earlier. Mass of the solute divided by mass of solution. Mass of solution would ideally mean the addition of the mass of the solute and mass of the solvent. As I showed you earlier, when you're talking about solution, a solution consists of solute and solvent. So when you're talking about the mass of solution, when you talk about mass of solution, it is the addition of the mass of solvent and solute. So that is what we have signified here. And then if you move on to the next slide, you can see if the mass of the solute is very small compared to the mass of the solution, the composition of the solute can be expressed as follows. So composition of the solution actually can be expressed as follows. So instead of writing it as number of parts per 100, that's what we do when you write it as a percentage. Whenever you use the word percentage, we are talking about how many parts of something is present per 100 parts of something else. For example, when you say the mass percent is 15 for a sodium chloride solution, what we talk about is per 100 parts of the solution, there are 15 parts of sodium chloride, right? So to very clearly see that, when we say that there is 15 grams of NaCl here in a solution that contains, now imagine the water percentage or water mass is 85 grams. The overall solution has a mass 100 grams. So the mass percentage, as we calculated earlier, is going to be calculated by taking the mass of the solute 15 grams divided by mass of the solution 100 grams. Mass of the solution was obtained by adding these two together. And then we multiply this by 100. So this communicates, when you write 15%, mass percentage is 15%. This communicates if you take 15 or if you take 100 parts of this solution, 15 parts out of this solution is going to be sodium chloride. Meaning, if you take 100 grams, one part being equal to 1 gram, if you take 100 grams, denoting 100 parts, out of these 100 grams, 15 grams is going to be sodium chloride. What about if you take, in a solution like this, if you have in a larger scale, if you take 100 kilograms, if you take 100 kilograms, then one part is going to be equivalent to 1 kilogram. So out of these 100 parts, 15 parts is going to be sodium chloride. Meaning, if you take 100 kilogram solution of this particular solution, 15 kilograms out of that 100 kilograms is going to be sodium chloride. The rest is going to be water. Is it clear, students? I hope this is very clear. However, imagine now in this situation, the solute mass is somewhat significant compared to the mass of the solution. So its mass was in grams as well as the solution mass was also in grams. 15 grams is the mass of solute and 100 grams was the mass of the solution. So a significantly higher mass, right? But imagine a situation where you have very small mass. You have a very small mass of, we'll take sodium chloride for this matter as well. Imagine you have very small mass of sodium chloride dissolved in, let's say we have overall solution's mass. Let's say overall solution has a mass of 100 grams, and the sodium chloride in the solution, now the solution is already formed. Imagine the sodium chloride that is in the solution had a mass of 0.01, or we'll say 0.1 grams. That's easier. 0.1 grams, or if you want to go even smaller, we can take 0.01 grams. So this is a significantly smaller mass of the solute compared to the mass of overall solution. So if you calculate the mass percent here, right, mass percent is basically parts per 100, or if you take 100 parts, how many parts are going to be the solute is communicated using mass percentage. Because you are multiplying by 100, we talk about per 100 parts. That's why we say percent per 100. So a mass percent is basically, if you want to call it another name, you can call it parts per 100. So mass percent is equivalent to parts per 100. It's going to be the mass of solute, which is going to be 0.01 grams divided by 100 grams mass of the solution multiplied by 100. Right? So at this point, you will get to this answer. This will cancel off. So it's going to be a smaller value, very small value. Mass percent is going to be 0.01. Instead of talking about such a small number, we can talk about the composition of this type of solution, where the mass of the solute is significantly small compared to the mass of solution. We can use a different type of method to calculate its composition. That is known as parts per 1000. Instead of using parts per 100, we are going to be now using parts per 1000. So in parts per 1000, we are going to multiply the mass of solute. We are going to first take mass of solute divided by mass of solution, as we did in the previous step as well. And then instead of multiplying this with 100, earlier on to calculate parts per 100, we multiplied it with 100. Now, since we want to find out parts per 1000, instead of multiplying with 100, we are going to multiply it with 1000. So at that point, what you get is parts per 1000. So 0.01 grams was the mass of the solute. Mass of the solution was 1000 grams. And this multiplied by 1000. Mass of the solution was not 1000 grams, 100 grams. And this has to be multiplied by 1000. So at that point, we get to parts per 1000. So this is going to be 0.1 ppm. 0.1 ppm. Right. So this is another way of communicating the composition when the amount of solute is having a significantly smaller mass compared to the mass of the solution, compared to the mass of the solution. So that's what we have done here. Students, you can now see that this is the formula that we can use to calculate parts per thousand. And as you can see, parts per thousand can be kept in two different units, either grams per kilogram or milligrams per gram. Because if you take a look at this between these two units, the difference is 1,000, right? When you talk about grams and kilograms, difference between the two units is 1,000. A kilogram is 1,000 grams. So this particular unit can be used to talk about parts per thousand. And same here. Milligram and grams also have a difference of 1,000 milligrams, or if you take 1,000 milligrams, it will be equal to 1 gram. So that's why we use this unit as well. We will talk about how this can be applied to our previous example. So let's go to our previous example here. You can see in the previous parts per thousand example, sorry students, this has been kept as parts per million. It was a small mistake. You can't keep it as ppm. ppm stands for parts per million. I have mistakenly kept it as ppm. We were talking about ppt, parts per thousand, so it should be t here, right? So please make note of that. So over here you can see when we were substituting values, we substituted values in grams, but the unit can be kept as milligrams per gram. 0.1 milligrams per gram. This unit is also applicable to this particular calculation. So similarly, we can use grams per kilogram as well. Based on the type of calculation you are dealing with, we can use grams per kilogram as well. Then you can use parts per million. For example, amount of specific pollutant in the atmosphere can be quoted with parts per million. So it can also be written as milligrams per kilogram as well. That is also another thing that you can do. We'll do a small example so that you understand this better. For example, let's say you have let's say in 1 kilogram of air, right? If we say in 1 kilogram of air, we say that there is let's say 2.5 into 10 to the power minus 6 many kilograms. So if you have this many kilograms of a specific pollutant, right? Then at that point, now air is going to be your overall solution. So in 1 kilogram of air, if you have this many kilograms of a pollutant, you can see compared to the overall mass of the solution, the solute mass is extremely small. So therefore, when you're calculating the mass percentage, what you're going to obtain is a very small percentage. Instead of talking about mass percentage, you can actually talk about parts per million here, because this number is significantly small. So you can use parts per million. Again, we will take the mass of the solute, mass of solute. You should know, students, by now air is a solution, and mass of the solution is going to be the mass of the air we considered. Multiplied by, now when we were talking about parts per 100, we multiplied by 100. When we were talking about parts per 1,000, we multiplied by 1,000. When we are talking about parts per million, the co-equation for calculating ppm, pph, ppt remains the same, which is basically the fraction between solute mass divided by mass of solution. But the number that we multiply this fraction is going to change. When it comes to parts per million, we multiply it by a million, or in other words 10 to the power 6. So at that point, mass of the solute is going to be, I wrote 2.5 into 10 to the power minus 6 kilograms divided by 1 kilogram, which is the mass of the solution, and then you multiply this by a million. So you can see kilograms cancel off, million and 10 to the power minus 6 cancel off, to give you 2.5 parts per million. 2.5 parts per million. If you kept this as a mass percentage, it's going to be extremely small value. So instead, keeping it like this is going to be more useful. So another way in which they say that we can keep this same answer is milligrams per kilogram. Milligrams per kilogram is also another way in which you can keep the same answer. So as you saw in the previous example, we can actually find out, instead of finding out the mass percentage, we can actually find out parts per million by multiplying with million. So the main core of the equation, mass of the solute divided by mass of the solution, didn't change. Only thing that changed was that instead of multiplying the fraction with 100, we multiplied with a million. So at that point, if you want to keep it as an SI unit instead of ppt or ppm, we can employ these units, milligrams per kilogram or micrograms per gram also can be used. So those are possible options that you have when it comes to talking about parts per million. And then we have parts per billion, again the same concept, when the mass of the solvent is quite large and when the mass of the solute is extremely small, in let's say in 10 to the power minus 9 gram figures. So at that point, instead of using a mass percentage, you can use parts per billion, and you will be using, if you want to use a separate unit instead of using ppm, you can resort to using micrograms per kilogram. Micrograms per kilogram. The difference between micrograms and kilograms is going to be 10 to the power 9. Micro stands for 10 to the power minus 6. Kilo stands for 10 to the power plus 3. So the gap between minus 6 and 3 is going to be, or gap between 10 to the power minus 6 and 10 to the power plus 3 is 10 to the power 9. So therefore, this unit can also be used to talk about parts per billion. In a similar way, we can use volume percent to calculate the composition of a solution. Now, just like when we spoke about mass percent, when it comes to the percentage of volume of a given solute in a solution, if the volume of the solute is extremely small compared to the solution, at that point we can use other units such as milliliters per liter, right? Milliliters per liter. Although just to be clear, sometimes we write it like this, but you will be using milliliters per liter. And we have microliters per liter when we're talking about parts per million. Again, the same concept, volume of solute divided by volume of mixture or volume of the solution into 10 to the power 6. When it comes to million, the value of million is 10 to the power 6. So we will be multiplying it 10 to the power 6 to get to parts per million. Now, when it comes to mass, when we were talking about parts per thousand, parts per million, we were talking about one part as a mass measurement. For example, if you are talking about parts per thousand, let's say we are talking about grams. At that point, 1 part will be equivalent to 1 gram. Now, if you have 150 grams of sodium chloride in a 1000 gram solution, we can say the composition is 150 parts per 1000. Out of the 1000 parts or 1000 grams that is found in the solution, 150 parts, or in other words 150 grams is sodium chloride. So that's why we say 150 parts per 1000. So at that point, 1 part was basically 1 gram. So the measurement was a mass measurement. Over here, the measurement is going to be a volume measurement. So when I say parts per 1000, we are talking about 1 milliliter or 1 liter. Any different type of volume measurements can be used here. So we are talking about volume measurements. So volume of solute divided by volume of solution or mixture multiplied by 1000, you'll get to parts per 1000. Another unit that can be used for parts per 1000 is milliliters per liter. And then you can see why we use milliliters per liter. Milliliters, basically milli stands for 10 to the power minus 3. So the difference between 1 milliliter and a liter is going to be 1000, right? 1000 milliliters is equal to 1 liter. So if you are keeping your final answer in milliliters per liter format, that means you are keeping the final answer in accordance with parts per 1000 format. And then we have parts per million. The same principle applies here. Volume of solid divided by volume of mixture or volume of solution multiplied by 10 to the power 6, resulting in microliters per liter unit. Or instead of using this unit, if you don't want to use this unit, you can just use ppm, parts per million. Now remember these units, students. In certain MCQ questions, they might be questioned. So one thing that you can do to remember is see the difference between these units. Usually the numerator will have the smaller unit. So microliters per liter. Micro stands for 10 to the power minus 6. So the difference between 1 and 10 to the power minus 6 is exactly a million. That's why we have this used as another unit for parts per million. We have parts per billion as well. Nano stands for 10 to the power minus 9. So a billion nanoliters is equivalent to 1 liter, right? So if you keep your parts per billion unit in nanoliters per liter, that means you're keeping your final answer in parts per billion format. So these are few ways in which you can keep, or you can actually present the composition of a solution. The composition of a dilute solution can be expressed using weight, volume, percentages. It can be expressed as ppm, which is parts per million or parts per billion. These can also be expressed in milligrams per decimeters cube, right? Milligrams per decimeters cube, and in micrograms per decimeters cube respectively. Parts per million, parts per billion can also be kept in these formats as well. The metric prefix is used to distinguish the difference between unit size. It is useful for describing quantity in a more scientific way. So you students, when it comes to talking about metric system, one of the advantages of using the metric system is that it has prefixes that communicates different values. So we are going to learn about that in a second. For example, a glucose solution contains 1.25 moles of glucose per kilogram of water or solvent. Hence, molality. This is another word that is new to you. Molality. Molality refers to the amount of substance that is found in one kilogram of solution. So, molality of glucose solution is 1.25 moles per kilogram. So, molality is going to be kept in this unit. 1.25 moles per kilogram. You can see we have used a prefix here which is kilo. And these are some of the prefixes that we come across in the SI system. You would have now certain prefixes are used when the numbers are too large. For large numbers, for example, when you have 1000 grams, instead of saying 1000 grams, we can say 1 kilogram, right? Or if you have 1,000,000 grams, 1,000,000,000 grams, you have to use different prefixes to abbreviate this number. For example, dA stands for 10 to the power 1. Hectare or hecto stands for 10 to the power 2. Now, we don't usually see these much in use, but these prefixes are there, so be aware of them. And then we have kilo. Kilo is very familiar to us. Kilo stands for 10 to the power 3. Right? That's why we say 1000 grams. We say 1000 grams is equal to 1 kilogram. Now, 1000 stands for what, students? 1000 is basically 1 into 10 to the power 3 grams, right? This is 1000 grams. So, 10 to the power 3 has a prefix, kilo. So, 1, and this can be written as a prefix, kilo, and then we have our unit, grams. So, 1000 grams is basically 1 kilogram. So, that is why it's easier. Now, you can see instead of writing 1000 grams or instead of writing large numbers, we can abbreviate the number using these prefixes. We have mega 10 to the power 6, giga 10 to the power 9, tera 10 to the power 12, not 1 10 to the power 2, it is 10 to the power 12, 10 to the power 12. And then we have deci, centi, milli, micro, nano, pico, femto, atto. But if you know up to pico level, that is enough. So these are prefixes that we can use if the number is quite small. So at that point, when you're using, for example, I'm quite certain you're very familiar with milliliters, centimeters and all that. So deci, centi, milli, you can see what their prefixes are. Now we know that there are 100 centimeters in 1 meter. This is something that all of you are very familiar with. From a small age, you are very familiar with this. But why is 100 centimeters equal to 1 meter? Now, 100 stands for 10 to the power 2. Right? And centi stands for what? 10 to the power minus 2. So if I convert centi into a numerical figure, centi is going to be 10 to the power minus 2. And then after converting centi into a numerical value, I will keep meters as meters. So you can see 10 to the power minus 2 and 10 to the power plus 2 cancels off, leaving behind just meters. So 100 centimeters is basically equal to a meter. So that is another way, that the small example that we did, just to give you an idea how we sometimes use prefixes when converting between different units. So remember these. Milli stands for 10 to the power minus 3, micro stands for 10 to the power minus 6, nano stands for 10 to the power minus 9, pico stands for 10 to the power minus 12. And we have definitions here. First one is molarity, something you are very familiar with. The amount of moles of solute. Now, when you're talking about amount, we have to always take the amount of the solute in moles when it comes to molarity. So, amount of moles of solute in 1 decimeter cube solution is called molarity. 1 decimeter cube of solution is called molarity. The units are moles per decimeters cube, students. So this is the unit that we always use when it comes to the unit of concentration or molarity. Is going to be moles per decimeters cube, but the SI unit is moles per meters cube. So if you are converting moles per decimeters cube into moles per meters cube, you would see that the concentration is going to be a very small value. So because of that, we usually use moles per decimeters cube. So after talking about molarity, we move on to molality. Molality is basically the amount of moles, again, amount of moles of solute. We spoke about amount of moles of solute in the previous definition also. So amount of moles of solute dissolved in 1 kilogram of solvent is called molality. So there are a few differences. When it comes to molarity, we spoke about the amount of moles of solute dissolved in 1 decimeter cube of the solution. In this case, we are talking about the amount of moles of solute dissolved in 1 kilogram of solvent, not solution. In this case, it is solvent. Now, in this particular equation, you can see how we calculate molality, amount of moles of solute divided by the mass of the solvent. So, amount of moles of solute is divided by mass of the solvent. So you usually take 1 kilogram, so the unit comes as moles per kilogram. But if the amount of moles that we are talking about is extremely small, at that point amount of moles will be taken as millimoles. So at that point we have amount of millimoles of solute divided by mass of the solvent. Mass of the solvent will be kept the same, kilograms. So the final answer will come in a different unit, millimoles per kilogram. When it comes to concentration, or in other words, molarity, molality and molarity are two different things. So concentration is defined as the amount of solute per unit volume, right? And when it comes to concentration, we use molarity. So amount of solute is usually taken in number of moles, and the volume is usually taken in decimeters cube. So the final unit happens to be moles per decimeters cube. So this is the equation. We commonly refer to this equation as C is equal to number of moles divided by volume. C is equal to and divided by V. So now we move on to another slide over here. In a 1 moles per decimeters cube solution, 1 mole of solute is present in 1 decimeters cube of the solution, not the solvent. When it comes to concentration, we talk about the amount of moles of solute dissolved in 1 decimeters cube of solution. So we have to keep in mind it's not the solvent, it is a solution. According to that, in C moles per decimeters cube, C is an arbitrary number here, C moles per decimeters cube solution, C many moles of solute is present in 1 decimeters cube of the solution. if you know the amount of moles in a volume that we need to prepare, we can prepare the required volume of the solution needed. For example, assume that we want to prepare 0.1 moles per decimeters cube sodium carbonate. Then at that point, if the amount we need is 0.1 moles per decimeters cube sodium carbonate solution that has a volume of 250 cubic centimeters, we can easily do that by calculating the number of moles that should be present in one portion of this 250 cubic centimeter solution. Now we have the answer here, so move on to that now. When preparing 250 cubic centimeters of aqueous solution of 0.1 moles per decimeters cube sodium carbonate, the amount of sodium carbonate in that volume of the solution should be first calculated. So students, we will move on to a small explanation here. Imagine you have 0.1 moles per decimeters cube sodium carbonate solution. And what does this unit mean? What does this unit mean? 0.1 moles per decimeters cube. So when you're learning chemistry, students, always think about things in a bit of a more logical manner. The unit communicates something to us. The amount of moles in a single decimeters cube of solution. That's why we have the unit or part of this unit per decimeters cube. Meaning if you take exactly 1 decimeters cube of this solution, there will be 0.1 moles in it. So if this volume has 1 decimeters cube of sodium carbonate solution, that means inside this we have exactly 0.1 moles of sodium carbonate. So we are required to make only 250 cubic centimeters. Now 250 cubic centimeters is basically quarter of this volume. 1 decimeters cube is equivalent to 1000 centimeters cube. So 250 cubic centimeters means basically quarter of this solution. So in 1 decimeters cube of the solution, if you have 0.1 moles, in quarter of that solution you should have 0.1 moles divided by 4. What would the volume be? What would the number of moles be at that point? 0.025 moles, right? 0.025 moles. So you can calculate it in a more logical manner like that as well. But since we have the equations to calculate it, we can do so over here using the equations as well. When preparing 250 aqueous solution of 0.1 moles per decimeters cube concentrated sodium carbonate, the amount of sodium carbonate in that volume of solution is calculated in this manner. Now, what brought about this calculation? That particular calculation was brought about by this equation. I hope you remember this. So now they are saying we need to prepare a solution. They have given us the requirement. The concentration of the solution should be 0.1 moles per decimeters cube. But we don't need an entire decimeters cube volume of the solution. They are asking us to only produce 250 cubic centimeters. So you can easily calculate the number of moles that we need to do this by using this equation. Concentration is equal to number of moles divided by volume. We know the concentration we need. We know the volume we need to prepare. So number of moles is the only thing that we don't know. So we can find that out by taking concentration, multiplying it with volume. And that's what we have done here. We have the concentration multiplied by volume. So concentration is, if I rewrite this, 0.1 moles per decimeters cube. Volume is 250 cubic centimeters, but we can't substitute volume in cubic centimeters. We have to convert it into cubic decimeters. So to do that, you have to divide this by 1000. So when you do that, you get to this equation, and the final answer is going to be coming in moles. So the answer would be 0.025 moles. The reason why its final answer is going to be obtained in moles is concentration is moles per decimeters cube, and the volume is decimeters cube. They will cancel one another off, leaving behind just moles. Right. So afterwards, we can see the amount of sodium carbonate needed to produce this particular solution should be measured. So mass of sodium carbonate that we need is going to be taken using this equation. Again, students, if you know the number of moles of substance that you need to measure the mass of, you can calculate the mass that you need to measure using this equation. Number of moles is equal to mass of the substance divided by molar mass. So in this particular situation, we know the number of moles we need to prepare the solution. We know the molar mass of the compound. We don't know the mass that we need to measure. So to obtain that, we can use this equation. Number of moles multiplied by molar mass should give us the mass that we need to measure. So number of moles multiplied by molar mass gave us the answer, which is 6.25 grams. So we need to dissolve the required amount of sodium carbonate, which happens to be 6.25 grams, in water and prepare 250 cubic centimeters of solution. Does that mean we need to measure 2.65 grams of sodium carbonate and then take 250 milliliters of water and then mix them together? Is that what we are going to do? No. If you want to make a solution with exact concentration of 0.1, we would normally use a volumetric flask for this. So we will first take a clean volumetric flask, and with the use of a wash bottle, as you may see in the next few minutes when we move on to the lab how we do this. So we will transfer the solid directly onto the volumetric flask with the use of a wash bottle. We will wash down the solid into the volumetric flask, making sure all of the solid enters the volumetric flask, and then we will add water. Now when you're choosing a volumetric flask, first of all you need to choose the volumetric flask of the correct volume. Since we need to prepare a solution of 250 milliliters or 250 cubic centimeters, we need to take a volumetric flask with that particular volume, and then you are going to add water all the way up to the calibration mark of the volumetric flask. Initially you will add a little bit of water, and then you will dissolve the entire solid that is present inside the volumetric flask, and then you will continue to add more and more water all the way up to the calibration mark. You wouldn't add a single drop less or more than that particular mark. If you add a single drop more, you have to start the solution or start preparing the solution all over again. So when it comes to preparing a standard solution, that's how you normally do it. So thus 250 cubic centimeter standard solution of 0.1 moles per decimeter cubed can be prepared in the lab using this way. Here a known volume of solution was prepared by dissolving a known mass of the compound in water. So to prepare a known concentration, we needed to take a known mass of the substance and we need to dissolve that mass in a known volume of water. Right. So now we move on to learning about how to properly select sodium carbonate if you are ever going to make a standard solution. Now students, in the lab there are a few different types of solutions that you can prepare, and one of the most important types of solutions that you prepare in the lab are known as standard solutions. Now standard solutions are a type of solution where we know the concentration of the solution very accurately. So when you're preparing standard solutions, you need to make sure that you prepare it in such a way that the concentration of the produced solution is known very accurately. To prepare a standard solution, you require substances known as primary standards. So we will talk about primary standards and their details later on. So sodium carbonate is one such primary standard. However, sodium carbonate can be found in a few different forms in the lab. One is the hydrated form. We also call it the hydrous form. And then we have the anhydrous form of sodium carbonate. So to prepare our primary standard solution, we would normally require the anhydrous sodium carbonate. Otherwise, you will not be able to properly prepare your standard solution. The sodium carbonate standard solution should be prepared by using anhydrous sodium carbonate. Anhydrous sodium carbonate in the lab may become hydrated when exposed to air. Right? So if you're using a sealed container and if you're opening up for the first time, you can be very sure that it is anhydrous sodium carbonate. But if you are using a solid bottle where you have kept it open for a very long period of time, at that point you can't be certain that the sodium carbonate is anhydrous, because some of the water vapor might have entered the bottle and it might have made some of the sodium carbonate into the hydrated form. So therefore, you have to take the crystal sample and put it in a ceramic crucible and heat it to a temperature higher than 373 Kelvin. So to remove all of the water that are attached to sodium carbonate, you have to take the solid and then heat it to a temperature above 100 degrees Celsius for quite some time until you obtain a constant mass. Right? So whenever you are heating something to remove water, keep in mind you have to heat that particular substance until you observe a constant mass. So you heat it for a while and then you measure the mass, whether it has changed. If it has actually reduced in mass, don't settle there thinking I have removed all of the water in here. You have to heat it again and then again measure the mass. Then you will see the mass is further reduced. Are you going to settle there? No. You will heat it once more for a period of time, and then after that, once it's cooled, you will measure it again. And if at that point the mass has not changed, this is indicative of the fact that all of the water is removed. If there were more water molecules attached to the sodium carbonate, then the mass will have further reduced. So you have to repeat this process until you see no change in mass when you heat the substance. So you have to heat it until you obtain a constant mass. Then place in it in a desiccator and do not let it come into contact with any water. And after you allow the crucible to come to room temperature, you have your anhydrous crystals of sodium carbonate prepared. So you can use this anhydrous sodium carbonate crystals to prepare your standard solution. Do not prepare standard solution from hydrous crystals. So whenever you are preparing a standard solution, keep it in mind. Do not prepare your standard solution using hydrous crystals or hydrates of compounds, right? We have sodium carbonate 10H2O. That's a hydrated form of sodium carbonate. So those types of crystals or solids should not be used to form a solution like this. A primary standard solution should not be formed with the use of hydrated solids. Reasons. According to the definition, a primary standard should not be hydrated compounds, right? You should not be use a hydrated compound, or in other words, you should not be using a hydrate of a compound. The presence of the mass changes in hydrous compounds when weighing the mass quantity of the compound is another reason. So students, when you are having a hydrated compound, there can be different number of water molecules attached to each sodium carbonate. If you're talking about sodium carbonate, that is. So we can have sodium carbonate 10H2O, some could be sodium carbonate 5H2O. So there could be some sodium carbonate 1H2O, and there might be certain sodium carbonates that are not attached with any water molecules. So each of these different species will have different molar masses, but you wouldn't know which ones you are choosing when you take a spatula full of sodium carbonate and when you measure it in your triple beam balance or using an analytical balance. You would not know the actual molar mass of the sodium carbonate you take, because it could be a mixture of sodium carbonate 10H2O or sodium carbonate X amount of H2O or sodium carbonate anhydrous. So since you don't know the actual molar mass of the compound that you are taking, when you're measuring a specific mass of sodium carbonate that is hydrated, you cannot be sure about the number of moles of sodium carbonate that you measure, right? You can't be sure about the number of moles of sodium carbonate that you measure. So you don't know very accurately the number of moles that are found in the mass that you have taken. So therefore you can't be confident about the concentration of the solution that you have made. So that is why we would not proceed to use a hydrated form of a given standard primary standard like sodium carbonate to prepare a primary standard solution. We would not do that, because that would end up in producing a solution that the concentration of the solution is not very accurately known. So if you don't know the concentration very accurately, you cannot call it a primary standard solution. So the mass changes that can be found in an anhydrous solution might introduce errors into your mass calculations, leading to a solution of incorrect concentration. Some examples are there. So if you heat sodium carbonate to a temperature below 100 degrees Celsius, or 100 degrees Celsius is 373 Kelvin. So you can see if you heat it to a temperature below 373 Kelvin, most of the time it will end up forming sodium carbonate 1H2O. So sodium carbonate 10H2O turns into sodium carbonate 1H2O, and 9 water molecules will be released. But if you heat it to a temperature above 373 degrees Kelvin. Then what happens is you will form anhydrous. You will form anhydrous sodium carbonate. You will form anhydrous sodium carbonate and water. So water will be evaporated. You are going to be left with just anhydrous sodium carbonate. So if you want to obtain anhydrous sodium carbonate, you have to take the hydrated sodium carbonate and heat it to a temperature above 100 degrees Celsius for a period of time until you obtain a constant mass. So overall reaction is given here. Then we take a look at the standard solution definition. So the definition of standard solution is given here. Standard solution is a solution of accurately known concentration. Very important. Solution of accurately known concentration. We know the concentration very accurately. Accurately known concentration prepared from a primary standard. They contain a known mass of the compound and its volume is a known volume. A compound of high purity is usually used. So they contain a known mass, meaning when you are preparing the solution, we will measure the mass of the compound and we will know the mass of the compound very accurately because you will be measuring the mass of the compound using very precise or accurate equipment like triple beam balance or analytical balance. So we will know the mass of the compound very accurately and its volume is also going to be known very accurately. So we will be using equipment or volumetric equipment like volumetric flasks. So when you're measuring the volume of the solution that you are preparing using this type of volumetric equipment, volumetric glassware, we know the volume of the final solution very accurately. So we know the mass that we included in it very accurately and the volume of the final solution very accurately, resulting in a solution that we know the concentration of very accurately. But just knowing the mass is not enough. We have to make sure that the compound that we used to prepare this solution had a high purity. Imagine you measure the mass very accurately and do all of that correctly, but imagine the compound is only about 50% pure, meaning the remainder of the 50% is impure or other different types of impurities. Or do you have the same concentration that you calculated theoretically in the final solution? No. So when you are using a specific substance to prepare a primary standard solution, you have to make sure the compound or the substance that you take is taken in a high purity, or the substance should have a high purity. Substances that do not usually have a high purity cannot be used to prepare a primary standard. Primary standards. So this is about the types of compounds that we can use to prepare a primary standard solution. A primary standard is a compound that can be obtained in high purity. So high purity is important, as a solid or as a solution, or that can be stored stably or in a more stable manner with a precisely known composition. So you should know the composition of it very precisely. It should be obtained in high purity. It should be very stable. These are few of the criteria that needs to be fulfilled when you talk about primary standards. If they are not pure, if they cannot be stored properly, if they are unstable, so then if they can't be stored for a while without undergoing any change, then you can't use them as a primary standard. And apart from that, you need to know their composition precisely. Type of primary standard solution, or type of standard solutions. There are two types of standard solutions. One type of solution is known as primary standard solutions. The other one is secondary standard solution. Primary and secondary standard solutions. So when you talk about primary standard solutions, it is quite straightforward. You will take a solid that is identified as a primary standard. So to be a primary standard, it needs to have a high purity, it should be stable, and the composition of it should be known. So meaning, when I say the composition of it should be known, imagine when you're preparing any type of solid, or when you're extracting any type of solid, there might be a small percentage of impurities. So if the solid is not 100% pure, if it is containing even slight amount of impurities, that should be known to us. So usually you would see in certain reagent bottles something called assay, right, that communicates how pure the substance is, right? Some of them are 99.8% pure, some of them are 98% pure. So that means there is small amount of impurities as well, but 99.8 or 99 or 98% pure means they are having a high purity. If you have something like 50% pure, that is not going to qualify to be a primary standard. So primary standard solutions can be prepared by taking a primary standard and dissolving it in water to produce a solution of known concentration. So when you're producing a primary standard solution, the concentration is known due to measuring the mass of the primary standard very accurately and measuring the final volume of the solution very accurately. And then we have secondary standard solutions. So what are secondary standard solutions? So secondary standard solutions are solutions that are formed after titrating the solution against a primary standard. Now, if you ever make a solution like sodium hydroxide solution, sodium hydroxide is not a primary standard. So if you ever make a solution of sodium hydroxide, the concentration of the sodium hydroxide is not going to be very accurately known. You will have a rough idea about its concentration, but the concentration of that is not going to be very accurately known. But you can take that sodium hydroxide solution that you don't know the concentration of very accurately, and you can titrate it against a primary standard, and then using the information you obtain, you can calculate the concentration of the sodium hydroxide solution. So the concentration of a solution that you calculate after titrating it against a primary standard is going to be very accurately known. So after we take sodium hydroxide and titrate it against a primary standard, then we can calculate the sodium hydroxide's concentration very accurately. So these types of solutions that we prepare by titrating against a primary standard is known as secondary standard solutions. So in secondary standard solutions also, we know the concentration of them very accurately. However, we couldn't prepare the secondary standard solution by taking a known mass of the secondary standard and dissolving it in a known volume of water. Instead, we had to first prepare the solution that will have a roughly known concentration, and then you will take that solution and will titrate it against a primary standard solution, and using calculations you can calculate the actual concentration of this secondary standard solution. So in a secondary standard solution, students, you will know the concentration of the secondary standard very accurately, because we will produce a secondary standard solution after titrating it with a primary standard. So secondary standards are produced like that. So primary standards. A primary standard consists of the following properties of chemical or reagent. So the primary standard should be extremely pure. It should have a high purity. Stability should be high, meaning it should not react with air. It should not react upon exposure to sunlight, right? It should not undergo any other chemical alterations when it is being stored. So it should have a high stability as well. It should be anhydrous. You should not have the hydrated form of a substance and call it a primary standard. So usually a primary standard would have no water attached to it. So it should be an anhydrous, or it should not be a hydrate of a compound. It should have low water absorption. So that means it should not be hygroscopic. So there are certain substances that are hygroscopic, for example, sodium hydroxide. If you have ever weighed sodium hydroxide on a watch glass, you would notice when you're taking the sodium hydroxide pellets onto a watch glass, they don't appear to be shiny. They are matte looking white color opaque solids. But after a while you can see they are glistening. That is because they absorb water from the surrounding. So there's a water layer around the sodium hydroxide pellets after a while. So at that point you can't carry out a proper mass measurement, because as you measure the mass of sodium hydroxide, since it absorbs water from the surrounding, the mass will little by little increase. When you go for another scoop of sodium hydroxide in your container, as you bring it down to the scale, the sodium hydroxide pellets that were already in the scale now have absorbed so much of water, so the mass is not going to be accurate. So it should not be hygroscopic, must have a very high molar mass. The higher the molar mass, the lower the percentage error of the mass measurement. So having a higher molar mass is good when it comes to being a primary standard. It should be easy to weigh. It should not be very difficult to weigh. Easy to weigh means if it is easily dispersed without being able to measure it properly, then it's going to be a problem. So ease of weighing is one other factor that we look into. It should be relatively available for use. If it is something that is extremely difficult to find, you can't use it all the time, so it's going to be a problem. It should not be toxic, and it should be not very expensive, because we will be using primary standards all the time. If it is extremely expensive, at that point the use of the primary standard will be difficult. So therefore these are the main criteria that are there when we are choosing a primary standard. Sodium carbonate NH2O crystal should not be dissolved to prepare a sodium carbonate primary standard. Now we explained why this is. A hydrated compound should not be taken as a primary standard. A primary standard solution of magnesium sulfate cannot be prepared by magnesium sulfate 7H2O. So same goes to magnesium sulfate. If you have a hydrated compound, can we prepare primary standards with those kind of hydrated compounds? Answer would be no. Some examples of primary standards are given here. As a primary standard for volumetric solution analysis, the following can be used. For acid-base titrations, we can use potassium hydrogen phthalate, right? To titrate bases, you can use potassium hydrogen phthalate. So like I mentioned earlier, when you are working with sodium hydroxide, you can't prepare a solution with accurately known concentration. So then whatever the sodium hydroxide solution you prepare, you have to titrate it against a primary standard. We usually use potassium hydrogen phthalate as a primary standard for bases. Potassium hydrogen phthalate looks like this. So potassium hydrogen phthalate will be used for titrating the solutions of sodium hydroxide or other bases to produce secondary standard solutions of those bases. Sodium carbonate, on the other hand, can be used to produce samples of secondary standard of acids. So if you want to prepare a secondary standard of acid, you can titrate it against a sodium carbonate, anhydrous sodium carbonate solution, which is going to be one of the primary standards we will be using in this experiment as well. This is the formula. Another form of the formula of potassium hydrogen phthalate is the same thing, students. So as I showed you earlier, potassium hydrogen phthalate is basically this, right? There are 6 carbon atoms in the benzene ring, so C is 6, and there are 6 hydrogen atoms around benzene as well, but 2 of the hydrogens are removed to attach these 2 groups here. So H4, and then we have COOH group and COOK group. This can also be written as, there are altogether 8 carbons, C8. There are altogether 5 hydrogens. 5 hydrogens, and you can see 4 oxygens, 1 potassium. So you can see the same formula here as well. Now, for acid-base titrations, you can use potassium hydrogen phthalate and anhydrous sodium carbonate. Anhydrous sodium carbonate is usually used when it comes to standardizing an acid solution. Potassium hydrogen phthalate, primary standard, is used when producing secondary standard solutions of bases such as sodium hydroxide. For redox titrations, the primary standards are arsenic oxide, sodium oxalate, potassium bromate, and KiO3, potassium iodide, and potassium dichromate. Precipitation titrations can be carried out by a simple salt like sodium chloride. So here is a list of some primary standards. So some examples of the primary standards that we use in the lab are given here. Anhydrous sodium carbonate, there's no water attached here. Sodium oxalate, borax, potassium dichromate, potassium bromate, potassium iodide, as we saw in the previous slide, potassium hydrogen iodide. We have arsenic trioxide and potassium hydrogen phthalate. So these are some of the common primary standards you will be using in the lab. So what are the uses of primary standards? We use them to standardize volumetric solutions, meaning we'll be using primary standards to carry out titrations and find out the concentrations of other solutions, and those other solutions will end up being known as secondary standards. To standardize solutions used in titrations, to standardize secondary standard solutions, and to calibrate analytical instruments. So for all of these purposes, we can actually use primary standards. So primary standards initially is actually mentioned to standardize volumetric solutions, meaning we can actually produce solutions with a well-known concentration, which is known as a primary standard solution. So we can actually produce those with primary standards, and then from there onwards we can use them for calculations, and from there onwards we can use them for titrations and standardizing of other solutions as well. Properties of secondary standards. Secondary standards consist of the following properties of a chemical or reagent. They have a lower purity than primary standards. So secondary standards usually have a lower purity compared to primary standards. Being of lower stability, they don't have a high enough stability. and they have somewhat of a high reactivity. And aqueous solutions of these are stable for long periods of time. So this is a must to be known as a secondary standard. As a solid, they might have properties where they are going to be somewhat reactive, they are going to be unstable when they are stored as a solid, and they will have lower purity as well. However, after a solution is formed, they should not be undergoing change for prolonged period of time. So they should be stable for a long period of time. If not, we can't use it as a secondary standard. Imagine we calculate the concentration of a solution with the use of a primary standard, and then in this second solution we would know the concentration of it really well. However, if this solution that we titrated is unstable, if it undergoes change when exposed to light, if it undergoes change when exposed to the air, so at that point, after a while, the concentration will again change. This is not going to be known as a good secondary standard. So even though the solution was prepared after a titration with a primary standard, you will not consider it to be a secondary standard if the secondary standard is not going to be stable for a long period of time when we have prepared the solution. So those are the properties of secondary standards. Now we move on to our experiment related information. In our experiment, we will need this equipment, and the only chemical that we need is sodium carbonate. In the lab, usually students, we will have sodium carbonate 10H2O, or sometimes even if you have anhydrous form of sodium carbonate, if it is kept open for a while, then we can't be sure about its composition. So it's always better to heat it until heat it to a temperature above 100 degrees Celsius until a constant mass is observed. So we have equipment here: volumetric flask, beakers, funnels, wash glass, 4-beam balance, wash bottle. Apart from these, a Bunsen burner will be needed if you don't have access to anhydrous sodium carbonate. Avoid touching the chemicals. Glassware should be well cleaned. So these are the precautions. When you are carrying out this experiment, you should not be touching the chemicals with your hands. I think by now it is common knowledge. You should not be touching any chemicals with your hands. Now students, we are going to take a look at the steps when it comes to preparing sodium carbonate standard solution. Like I mentioned earlier, before we start this experiment, if you don't have access to anhydrous sodium carbonate, you have to take the hydrated form of sodium carbonate. You have to heat it to a temperature above 100 degrees Celsius until a constant mass of sodium carbonate is obtained. So at this point, you have obtained anhydrous sodium carbonate. So allow it to cool down in a desiccator, and after that, you can use that sample of sodium carbonate to prepare your standard solution. So when you're initially preparing a standard solution, these are the steps. You need to know the concentration of the standard solution that you need to prepare. It is 1 moles per cubic decimeter. So first of all, you need to calculate the mass of sodium carbonate. You need to weigh. After that, you have to use the triple beam balance to weigh this. So before we start the use of triple beam balance, you have to make sure the triple beam balance is placed on a table and it is properly leveled. At that point, you can go ahead and place your watch glass on the metal plate or weighing pan of the triple beam balance. When you do that, the triple beam balance will no longer be aligning with one another. So then there are 3 notched beams in the triple beam balance, and as you know, there are things called sliders or riders that can be moved along each of the beams. So you can move them and observe at what positions that the triple beam balance arm is going to align with the line on the base. So as the two lines again, when they become aligned with one another, you have measured the mass of the watch glass. So if you say the mass of the watch glass is W, then if you know the mass of sodium carbonate that you should measure, for example, if you are going to prepare 1 moles per decimeters cube sodium carbonate solution, and the mass of sodium carbonate needed is 26.5 grams. So if you are going to measure 26.5 grams, now after measuring the mass of the watch glass, you know if you add 26.5 grams of sodium carbonate, what the overall mass would be. So by keeping the watch glass on the weighing pan, you can move the sliders until the value of all of the sliders added together actually provide the value of 26.5 added with the value of or the mass of the watch glass. So watch glass mass added with the mass of sodium carbonate should be entered into the triple beam balance first. Then again, it will not be aligning with one another once you set this particular mass in the triple beam balance. And from then onwards, what you're going to do is you're going to start adding sodium carbonate onto the watch glass until the triple beam balance aligns really well with the line that is found on its base. So at that point, students, you can see that you have accurately measured 26.5 grams of the sodium carbonate that we prepared earlier. So what you do is you have the triple beam balance here, there's your metal plate, and there's an arm here that needs to align with the line here. So first you will place your watch glass and take its measurement, and after that you will add to the triple beam balance. You will move the sliders to different locations, and you will get the triple beam balance to read the value that you get when you add the mass of the watch glass with the mass of the sodium carbonate. So you add them together and the final mass value should be entered into the triple beam balance with the use of sliders. At that point, this arm will actually point downwards. So then you'll have to keep adding sodium carbonate little by little until the arm comes back up to the correct level. So when it comes back up to the correct level, you have measured the right amount of sodium carbonate. So afterwards, you are going to transfer the sodium carbonate that you measured into a volumetric flask. You'll be using a funnel, right? And the sodium carbonate is going to be washed down using a wash bottle here. You are going to wash down the sodium carbonate into the volumetric flask. Now the volumetric flask you should choose over here is going to be 250 milliliter volumetric flask. And after transferring all of the solid, you are going to mix the solid really well until all of the solid dissolves. And then you are going to start adding more and more distilled water until now when it comes to the volumetric flask, the neck of the volumetric flask is quite narrow, and then there's going to be a calibration line like this. So your solution level should perfectly align with this calibration line. So you will keep your eye level should be at the same level as the calibration mark at this point, and you will start to add water little by little with the use of a dropper close to this point until the bottom of the meniscus. Now when water is present in a narrow area like this, you will very clearly observe a meniscus. So the bottom of the meniscus should align perfectly with this line. If you add we say if you overshoot or if you add a little bit more water than this level, then you have to start this process all over again. That means you have diluted the solution more than required. You can't just remove the water using a dropper quickly and say, I'm done. No, that is not possible. Then you have removed certain amount of sodium carbonate with the solution as well. So you can't say, I quickly took the drop off, so therefore this is okay. It is not. If you add even a single drop more than this calibration mark, at that point you are going to have to redo this whole thing, because you have added more water and you have diluted the solution. Even if you remove that additional drop will now carry a certain amount of sodium carbonate. So therefore the solution of your final volume is going to be different. So this is how you would transfer the solid into the volumetric flask, and then you will add water all the way up to the calibration mark. At that point you would have prepared now, depending on the concentration that you want to prepare, earlier on, actually there needs to be a correction here. It's 0.1 moles per decimeters cube concentration is what we're looking at, not 1 mole per decimeters cube, 0.1 moles per decimeters cube concentration. So at that point you would have now formed 1 moles per decimeters cube, not 0.1 mole, 1 moles per decimeters cube of sodium carbonate primary standard solution. So this is the way in which you can actually prepare a standard solution. If you want to prepare another standard solution such as sodium oxalate standard solution, you can prepare it in the following manner. First of all, we need to calculate the number of moles that are required to produce a standard solution of sodium oxalate with this concentration, and this is the volume that we require. So the volume is 100 milliliters and concentration is 0.2 moles per decimeters cube. So using the calculations we used earlier, we can calculate the number of moles that we need to prepare this particular standard solution. It happens to be 0.02 moles, and if you know the molar mass of sodium oxalate, this is the molar mass of sodium oxalate. If you know the molar mass of oxalate, the number of grams that you should measure, the mass that you should measure to prepare a standard solution of 0.2 moles per decimeters cube sodium oxalate can be calculated like this. So we need 2.68 grams. So you can accurately measure 2.68 grams of sodium oxalate into a watch glass, and using the method that I showed you earlier, we can transfer this solid crystals onto a volumetric flask with the use of a wash bottle and a funnel. So after that, you can dissolve all of the solids by adding a little bit more water, like I mentioned earlier, and then you can proceed to add water up to the calibration mark of the volumetric flask. Now keep in mind, students, whenever you are preparing a standard solution, the use of a volumetric flask is a must. You should use volumetric flask of the required volume. Now if you are going to be preparing a solution that has 100 milliliter volume, then you have to use a 100 milliliter volumetric flask. If you're going to prepare a solution of 250 milliliters, you have to use a 250 milliliter volumetric flask. So over here we can see, after transferring the weighed solid into 100 milliliter volumetric flask, you can add water all the way up to the calibration line, and then mix it really well to produce your standard solution. A primary standard aqueous solution of sodium oxalate can be prepared because sodium oxalate crystals are 99.95% pure, 99.95% pure, extremely high purity is there. So therefore we can very easily prepare a standard solution of sodium oxalate because it has a high purity Not just that, it is stable, right? It is not undergoing any decomposition when exposed to air or when exposed to light, and we know that it has a bit of a higher molar mass. So due to these properties that sodium oxalate has, we can use sodium oxalate for preparing a primary standard solution. And when it comes to preparing 500 cubic centimeters of sodium hydroxide, is sodium hydroxide a primary standard? No. Sodium hydroxide is not a primary standard. However, when you are trying to prepare a solution of sodium hydroxide with a specific concentration, you have to calculate the mass of sodium hydroxide that you should measure in order to produce this particular solution. You can then add this sodium hydroxide to 500 milliliters of water or to a volumetric flask that has a volume of 500 milliliters. But you have to know very clearly that this particular solution will not have the concentration that you are aiming to produce. Because when it comes to measuring the mass of sodium hydroxide, the mass measurement is going to be error-sum, meaning as you measure the mass of sodium hydroxide, certain amount of water molecules will get absorbed, or since sodium hydroxide is a hygroscopic substance, it will absorb water from atmosphere. So as you measure the mass of sodium hydroxide pellets you have taken into your watch glass, some of the mass that is seen in the analytical balance is coming from the water that is dissolved in sodium hydroxide. So it is not pure sodium hydroxide. So therefore your calculations are going to be wrong when it comes to calculating the actual concentration. So therefore sodium hydroxide solutions will not have a very accurately known concentration. So the amount of sodium hydroxide you would need to produce a solution that has this particular concentration, right? We are trying to produce a solution that has 0.2 moles per decimeter cube concentration. To produce that type of solution, you would need 4 grams of sodium hydroxide. So you measure this mass as quickly as possible to minimize the amount of water mass that you take into your measurement, and then you will proceed to make the solution. However, students, this is not going to be a standard solution. This is only going to have a concentration roughly equal to the concentration that you aim to prepare. In this way, 500 cubic centimeter sodium hydroxide aqueous solution of 0.2 moles per decimeter cube can be prepared in the lab, but this particular concentration is not going to be very accurate. If a student says the concentration of above sodium hydroxide aqueous solution can vary by a small amount, explain the reasons as to why sodium hydroxide cannot prepare a standard solution of the correct concentration. First reason, sodium hydroxide crystals absorb water in air. So sodium hydroxide absorbs moisture from air. So therefore, when you are measuring the mass of sodium hydroxide, the mass measurement is going to be wrong. Sodium hydroxide crystals absorb carbon dioxide in air. They can react with carbon dioxide in air when in solid form. So this will also result in some of the sodium hydroxide being spent and not in the sodium hydroxide form. So if you are measuring sodium hydroxide, not only it reacts with water but also with carbon dioxide in air. So in the mass that you measure, you wouldn't have the exact number of sodium hydroxide moles that you aim to have in that mass. This results in a wrong number of moles introduced into a well-known volume. So when you don't know the number of moles that are in a given volume, you can't actually talk about an accurate concentration of that solution. Finally, students, we have a few other substances that we can't use as a primary standard. So we are going to take a look at those now. So when it comes to sodium dichromate, it is not a primary standard. It is capable of absorbing water vapor from air. so it is hygroscopic. It will absorb water vapor from air. You can't use sodium dichromate as a primary standard. Potassium permanganate is not a primary standard. Inability to obtain KMnO4 in a very high pure condition. We can't obtain potassium permanganate with high purity. It is an oxidizing agent, so it oxidizes substances that it comes into contact with. So it is not going to be we can't use it as a primary standard, because as it comes into contact with other agents, it's a very strong oxidizing agent. So therefore, after a while, when it reacts with things that are coming into contact with potassium permanganate, it will spend some of the potassium permanganate to oxidize the other reactants that it comes into contact with. So we can't properly keep it stored, as it is a very strong oxidizing agent. KMnO4 reacts with various organic substances in air, oxidizes it to MnO2 in neutral or alkaline medium, like I mentioned earlier. So MnO2 or neutral in alkaline medium, or in acidic medium, KMnO4 will reduce itself into Mn2 plus while oxidizing others. So this is another reason why we can't use KMnO4 as a primary standard. And decomposition of KMnO4 under sunlight. When KMnO4, potassium permanganate, is exposed to sunlight, it can undergo decomposition. This is also another reason why we can't use KMnO4 as a primary standard. Reasons why we can't use sodium thiosulfate as a primary standard. We can't obtain sodium thiosulfate crystals in very high purity, so it is low in purity. When it comes to sodium thiosulfate, the first reason we observed was sodium thiosulfate cannot be obtained in high purity. Apart from that, sodium thiosulfate is hygroscopic. It absorbs water from the surrounding, so therefore even that is going to be a problem when it comes to measuring the correct mass of sodium thiosulfate needed to produce a solution with known concentration. So these are the reasons why we can't use sodium thiosulfate, potassium permanganate, and sodium dichromate as primary standards. Now students, we have discussed a few details revolving around experiment 4. We have learned how to carry out the experiment 4, but we have to actually move into the lab and conduct these experiments to learn how we actually carry out such experiments. So students, it's time for us to move on into the lab and learn about how to use the triple beam balance and learn how to prepare primary standards. So let's go on ahead and move into the lab and actually conduct these practicals. GCE Advanced Level Chemistry Practical Series, experiment number 4, preparation of standard solutions. In this practical, we are going to learn how to use or how to handle glassware, how to use a triple beam balance, and we are going to teach you how to measure volumes as well as how to prepare a solution of a particular concentration. Now let's move on to the reagents and the equipment we will be using for this practical. In this practical, we will be using sodium carbonate. What we have here is sodium carbonate 10H2O. We'll be using this to prepare our standard solution. And to weigh the right amount of sodium carbonate, we will be using a triple beam balance. We can also use a digital balance like this one, so we will be using that as well. And we will be using a 250 milliliter volumetric flask, a funnel, a watch glass, and a wash bottle containing some distilled water. Now, let's move on to our experiment. In this practical, we will be using our triple beam balance for the first time. So, let's learn how to use it. Before we use it, we have to identify the parts that is present in this triple beam balance. We have our base here, so everything that you see on this triple beam balance is present connected to our base. And here we have our stainless steel weighing pan. So we will be placing whatever the objects that we need to weigh on top of this weighing pan. And you can see over here there are 3 notched beams. The first notch we see here goes from 0 grams to 100 grams with 10 gram graduations. And we have our second beam. It goes from 0 grams to 500 grams with 100 gram graduations. And then finally, we have the last beam over here that goes from 0 gram to 10 grams with 1/10 of a gram graduation. When using the triple beam balance, we have to make sure the line you see over here, you can see a straight line over here, and on this part of the triple beam balance, you see a line with a 0 written next to it. So these 2 lines indicate us whether the triple beam is balanced or not. When measuring a mass using the triple beam balance, we have to make sure the 2 lines you see over here, should balance. The line that you see on the beam of the triple beam balance should align perfectly with the 0 line over here. When it aligns like that, it indicates that the triple beam is now at a balance. So whenever you place something such as this watch glass on the triple beam balance, we can see the 2 lines now no longer align. This indicates that this side of the balance is heavier. So to balance it, we will be moving these metal pieces that is connected to the triple beam, which are known as riders, or sometimes we call them sliders as well. So when you keep on moving them, at one point, we get to the point where the 2 lines will balance once again or align once again. So at that point, we can say we have accurately measured the mass of this watch glass. Now, let's start measuring the mass of this watch glass accurately. So in order to do that, I will have to turn this towards myself. Before we start this experiment, we have to make sure the 2 lines align perfectly. If they do not align perfectly, there is an adjustment knob over here. We can use this adjustment knob to make sure the 2 lines align perfectly before we start our experiment. When we have noticed that the 2 lines present on the arm of the triple beam balance and the base of the triple beam balance are now aligned, we can move on to weighing the mass of this watch glass. So in order to observe if the 2 lines perfectly align, you have to bend down and take your eye level to the level of the 2 lines and observe if the 2 lines are perfectly aligning. You should not observe it while standing up like this, because you will not be able to get a clear enough view of the 2 lines standing upright like this. After observing that the 2 lines are perfectly aligning, we can place our watch glass on the triple beam balance. As you place the watch glass, you can see the arm has now moved up. This is no longer aligning with the zero line present on the base of this triple beam balance. So now, to make it come to that alignment again, we can start moving these riders. We first start with the middle beam, where it has 100-gram graduations. So we will move this rider in the middle beam. When I moved the 100-gram rider, you can see now the beam is at a position that is way below the 0 point, meaning that this watch glass is definitely lighter than 100 grams. So we move it back, and then we start moving the 10-gram rider. So we move it to the 10-gram position. We do not see a movement here, so we move on to the 20-gram position. Again, still no movement. We can move it to the 30-gram position. We do not see a movement, so we move it to the 40-gram position. As you can see, when we moved it to 40 grams, the triple beam balance is no longer in balance again, but this time around it indicates the right hand side of the balance is heavier than the left hand side, telling us this watch glass is not as heavy as 40 grams. So we move it one notch backwards. As you can see, there are notches on the triple beam balance. Now it is at 30, and now we finally move on to the last beam of the triple beam balance, where there is 1/10 of a gram graduations. So this last beam, we can very carefully move the rider to see at which point this beam will come down from this position and balance with the 0 line. We can do it slowly. We can see the beam is starting to move downwards, but still did not align with the 0. That means we have to move the rider further to the right hand side. As you can see, when we are trying to balance this mass over here and get the reading, the pointer of the triple beam balance starts to oscillate up and down. And when we have accurately measured the mass of this, these oscillations will happen in such a way that the center point of these oscillations balance or align perfectly with the 0 line of this triple beam balance, indicating that we have accurately measured the mass of this watch glass. So right now we can see the oscillations have come to a stop, and at the same time the pointer of the triple beam balance aligns perfectly with the 0 line of the triple beam balance. So now we can move on to measuring the right amount of sodium carbonate using this reading. Before that, let's take a look at what the reading here is. So our first beam reading is at 30, indicates we have taken 30 grams there, and the second beam is at 0, and the third beam is at 8.7. It is at 8.7 exactly. So this reading is 38.7. So we have this watch glass that has a mass of 38.7. Now, this triple beam balance has given us a reading because the pointer aligns with the zero line, and that reading is 38.7. We have our first beam rider on the 30th gram position and the last beam rider on the 8.7 position, and the second beam rider was not moved because this was not heavier than 100 grams. So the final reading as it stands is 38.7 grams. Now let's take a digital balance. What we have here is a digital balance. We can use digital balance as well when it comes to measuring masses within a lab environment. So now let's take our watch glass and place it on our digital balance and observe if we get the same reading. First of all, our digital balance reads 0 and the measurement unit is grams. Always check that because sometimes certain digital balances give you measurements with different units. So then you have to adjust the digital balance in order to get to the unit that you want. So we have grams here and it reads 0.00. Now let's take our watch glass and place it on our digital balance. Now when we placed the watch glass on our digital balance, we saw the reading we obtained was 38.70. The same reading we obtained using our triple beam balance. This tells us the reading that we obtained was accurate because we used two methods for measuring the mass of this watch glass, and both the methods gave us the same reading. Now let's move on to measuring the right amount of sodium carbonate. Now we are about to prepare a standard solution and we are going to measure the sodium carbonate we need to prepare this standard solution. So what is a standard solution? A standard solution is a solution where we know the concentration quite accurately. When it comes to preparing a standard solution, you will be using a primary standard. So there are few qualities of a primary standard or solid that is used as a primary standard. Usually students, a primary standard should have a high purity. It should be quite stable. Apart from that, a primary standard should be anhydrous. It should be not hygroscopic, meaning it should not be absorbing water from the surrounding. So if the solid absorbs water from the air, or if it absorbs moisture from air, it is not going to be suitable as a primary standard. Apart from that, it should have a high molar mass. It should be non-toxic. It should be easy to weigh. It should be commonly available and inexpensive as well. So these are the properties that should be found in primary standards. To summarize, primary standards should have a high purity. They should be stable. They should not be hydrated compounds, so they should be anhydrous. They should not be hygroscopic. They should have a high molecular mass. They should be easy to weigh. They should not be toxic. Apart from that, they should be quite inexpensive and commonly available so that we can carry out this type of reactions easily. So students, these are the common properties that you see in primary standards. Now, after going through the list of properties that a primary standard should have, When we observe the sodium carbonate that we have here in the lab today, you would notice something. The sodium carbonate we have in the lab today here is not a primary standard. Why is it not a primary standard? Because it has 10 water molecules in each sodium carbonate, meaning that this is a hydrated compound. Sodium carbonate 10H2O. This is not an anhydrous compound. Primary standards should not have any water bound to them, because at that point you can't be very sure about the mass of sodium carbonate present in a sample of sodium carbonate 10H2O. Certain sodium carbonate might have 10H2O with them. Some might have a lower number of water molecules attached to its sodium carbonate. This might introduce some errors when it comes to calculating the exact number of moles of sodium carbonate present in a sample that we have measured. So therefore, students, it is always preferred to obtain a anhydrous sodium carbonate sample when you're trying to produce a primary standard solution using sodium carbonate. You can prepare an anhydrous sodium carbonate sample using this sodium carbonate 10H2O we have here. We will take a small mass of sodium carbonate 10H2O and we will transfer it onto our crucible here. Like I mentioned earlier, we will heat it then to a temperature of 373 degrees Kelvin and above. So you have to heat it to a higher temperature, and then if you heat it for about 45 minutes, all of the water will be removed from the sample. In other words, you can heat the sample to a higher temperature than 100 degrees Celsius until a constant mass is obtained. So if you heat it for about 45 minutes, we can actually be sure that all of the water is removed from the system. But if you don't want to wait that long, you can actually heat it to a temperature greater than 100 degrees Celsius, and you can constantly measure the weight of this sample, and by the time that you obtain a constant mass, you can be sure that all of the water is removed from the system. So now we are going to be doing that. So we have our sodium carbonate that we have in this bottle here, sodium carbonate 10H2O, and we will be transferring a small amount of sodium carbonate onto our crucible here. Now what we transferred was sodium carbonate 10H2O, and now we will be heating this sodium carbonate until all of the water in the sodium carbonate 10H2O is removed. Now we are going to use a Bunsen burner to heat this sodium carbonate sample. So we use a crucible here because we are going to subject this sample into somewhat of a higher temperature, a temperature greater than 100 degrees Celsius or temperature greater than 373 degrees Kelvin. So therefore, we will be using a crucible here, and we will heat this up until all of the water is removed. So we will be heating this up for about 45 minutes, and I will meet you again after we have heated the sample for long enough to remove all of the water from the sample. Now students, we have heated the sodium carbonate 10H2O sample that we took into our crucible for about 45 minutes, and we have allowed it to cool down as well. Now it is cool to the touch, you can touch it because it has cooled down to room temperature. So we have now prepared our sodium carbonate sample. It is no longer having any water in it. So this is our sodium carbonate anhydrous sample. Sodium carbonate anhydrous sample. I will take a small amount into the petri dish, leave the rest in the crucible itself. So we have now prepared our primary standard, which is sodium carbonate without any water in the sample, or in other words, anhydrous sodium carbonate. So students, we are going to prepare 250 milliliters of sodium carbonate solution, and the concentration of the solution should be 0.1 moles per decimeters cube. So to prepare 250 milliliters of this solution, we will be using this volumetric flask that can measure very accurately all the way up to 250 milliliters. So now let's calculate the mass of the sodium carbonate. We need to prepare a 0.1 moles per decimeters cube concentrated sodium carbonate solution. Now the molar mass of sodium carbonate, anhydrous sodium carbonate, is going to be 106 grams per mole, and we are about to prepare 0.1 moles per decimeters cube concentrated solution. So if you are going to prepare 1 decimeters cube of this 0.1 moles per decimeters cube concentrated sodium carbonate solution, you would need 0.1 moles of sodium carbonate dissolved in 1 decimeters cube of solution. However, we are not going to be preparing 1 decimeters cube of this solution. Instead, we are going to be preparing quarter of that, meaning we are going to be preparing 250 milliliters or 250 cubic centimeters of this solution. So for 1 decimeters cube, if you need 0.1 moles, for a quarter of that volume, you would require 0.025 moles. And we know the number of moles we need, and we know the molar mass of the substance. So therefore, we can calculate the mass of sodium carbonate needed to prepare 0.1 moles per decimeters cube concentrated solution if you are going to prepare 250 milliliters of this solution. So since you know the number of moles we need and the molar mass, if you multiply 0.025 with 106 grams per mole, you are going to obtain a value of 2.65 grams, which is going to be the mass we need to measure to prepare this solution. So in order to do that, students, we have our triple beam balance we used a little while ago. So on this triple beam balance, we measured the mass of our watch glass. Now watch glass had a mass of 38.7. So you can see it still present here, 38.7. You can see on the top beam over here, the slider is at the 30th notch, meaning this reads 30 grams, and the bottom slider is at 8.7, indicating that the total of, or indicating the reading of this particular triple beam balance as it stands now is 38.7. So that is the mass that this particular triple beam reads right now, because the mass of this watch glass we have over here is 38.7. We confirmed it using a digital balance as well. So now we need to measure 2.65 grams of sodium carbonate. In order to measure this, we need to first add 2.65 to 38.7. So when you add 2.65 and 38.7, it happens to be, when you calculate it, it will get to the value 41.35. 41.35. So we need to first adjust these sliders so that this triple beam balance reads 41.35. After adjusting it in that manner, we will start to add sodium carbonate to our watch glass here until these two lines that we see here in the triple beam balance, the line that is on the arm of this triple beam balance and the base of this triple beam balance, until they align perfectly, we will add sodium carbonate to our watch glass here. So students, let's get the reading that we have over here in the triple beam balance up to 41.35. So are we going to move this middle slider? If you move it one notch to the left, it will read 100. Do we need to measure 100 of anything here? No, we need to measure 41.35. So we need to get these values to 41.35. So easiest way to get to 40 would be to move this top slider over to 40. Now when you move it to the correct location, you can hear that it falls into the correct notch, and you can see that it is at 40 now. And then we want this bottom beam, the slider at the bottom beam, to read 1.35. So if you bring it over here, it is now at 1, and then if you move it a little bit further, it becomes 1.3, and right between 1.3 and 1.4 would be 1.35. Now students, we have adjusted the reading of this triple beam balance to 41.35. 41.35. So now it is up to us to add sodium carbonate until the line that you see over here. Now it is not aligned, right? You can see it is now below this line that we have on the triple beam balance. The arm of the triple beam balance is now pointing further down, so therefore the two lines are not aligned with one another. As we add more and more anhydrous sodium carbonate onto the watch glass, you can see the triple beam balance is gradually, or the arm of the triple beam balance will gradually come up, and you will see that they will start to align once more. We will continue to add sodium carbonate, anhydrous sodium carbonate, until we see that these two lines align with one another. You can see at this point, you can see it has moved up a little bit. The arm of the triple beam balance is now gradually aligning with our two lines. The arm of the triple beam balance is gradually aligning with the line on the base. So we have to add a little bit more. Now at this point, students, we can see it has aligned with the line in the base. So the two lines are now aligning perfectly, meaning it is now balanced, indicating the mass that we have measured over here is having a total mass of 41.35. And we know out of this 41.35 total mass, 38.7 grams comes from the watch glass. The remainder, which is 2.65 grams, came from our sodium carbonate sample we added to this watch glass here. Now students, since we have measured our sodium carbonate sample accurately, not just any sodium carbonate, anhydrous sodium carbonate sample accurately, we can now move on to transferring this solid sample onto a volumetric flask to prepare our standard solution. So let's go ahead and do that. So let's move this out of the way for a while. Now we have our 250 milliliter volumetric flask, and you can see that there is a calibration mark over here. The calibration mark over here is etched onto the neck of our volumetric flask, and we have already learned when handling volumetric equipment you have to be very careful, because these equipment are properly calibrated at a specific temperature. In this case, this particular volumetric flask was calibrated at 20 degrees Celsius. So students, when you are handling them, be careful, don't keep it in the vicinity where you will be having a lot of movement, because you can easily knock them off. And when you are handling them, don't touch them from the neck over here and then start to swirl solutions around like so. Don't do that. And make sure the volumetric flask that you get is properly washed and dried. So students, we now need to transfer this solid sample into this volumetric flask. In order to do that, we will be using a funnel and a wash bottle. This wash bottle contains distilled water. So first we will be placing our funnel on the volumetric flask like so. But if you start transferring liquids while the volumetric flask and the funnel is placed like this, the only opening that you create is the opening that is found in the middle of the funnel. So as water or whatever the liquid goes in, the air that is replaced in the volumetric flask should come out from the same opening. So when that happens, you might see a small amount of water splashing around, because as water enters this volumetric flask, there will be a certain amount of air that is trying to escape the volumetric flask as water is replacing the air in the volumetric flask. And this region is completely sealed by the funnel, so therefore only this opening will allow the air to escape. So it is not ideal to just place it like this and then start pouring in your water to this. So whenever possible, lift it up a little bit and then start pouring in water, or in this case we are transferring the solid with the use of a wash bottle. So when you're doing that, lift up the funnel a little bit so that there will be enough space for the air to escape from the volumetric flask. Now let's take our solid sample, and we have to place the solid sample like so, and we can lift it up. You can see now I can move the funnel along with the solid sample here, and then with the use of a wash bottle you can wash down this solid onto our volumetric flask. You can see we can gradually wash it down onto our volumetric flask like so. You have to make sure the entire surface of the wash glass is completely washed. Afterwards, you can turn the wash glass around and wash the back of the watch glass a little as well, to ensure all of the sodium carbonate solid is transferred into our volumetric flask. Afterwards, you can wash the inside of the funnel and the tip of the funnel as well. After that, students, we can move on to observing what is present in our volumetric flask here. After keeping the funnel and the watch glass aside, we can now observe what is present in our volumetric flask. We can see there is some solid still undissolved in the volumetric flask. So the first thing you can do is to mix it really well. So when you're mixing, don't hold the volumetric flask from the top like so. So this neck area of the volumetric flask could break if you apply enough force. So therefore, do not swirl the volumetric flask around by holding it from the top of the volumetric flask. You have to hold the volumetric flask from the base of the neck of the volumetric flask like so. And then you can mix the contents in the volumetric flask by swirling the solution around until all of the solid dissolves. Now we can see almost all of the solid is dissolved. We can add a little bit more distilled water with the use of a funnel. And you can continue to mix it until all of the solid is completely dissolved. Now we can see that all of the solid is completely dissolved. There is no solid particles inside this volumetric flask. You don't see any solid particles inside this volumetric flask. So now we can proceed to add water all the way up to this calibration mark. When you're adding water, students, be careful if you're adding water with the help of a beaker. If you maintain a specific rate of addition of water, you will notice that this area where there's a larger, wider base, filling water would take some time, but as you pour water in the same constant speed, the remainder of the area will get filled very quickly. Especially once you reach the neck area, this neck area will get filled very, very fast. So therefore, you need to control the addition of water based on where the water level is. So after you get to this area, you can add water very slowly all the way up to the calibration mark. But afterwards, you can start adding water with the help of a dropper. We have a dropper here. We'll be using this dropper to add water close to the calibration mark. So let's use a funnel and we can proceed to add water gradually with the use of this funnel. You can see we can gradually add water onto our volumetric flask. Always use distilled water. Now I'm controlling the amount of water that I add. As you can see, we are at the neck area of the volumetric flask. From this point onwards, students, you can use a dropper to add the right amount of water until the bottom of the meniscus aligns perfectly well with the calibration mark that we have over here. So you can lift the volumetric flask up to your eye level. We will add water drop by drop until the last few drops. When you're adding the last few drops, to make sure that you very accurately add the last few drops, to make sure the bottom of the meniscus aligns perfectly well with the calibration mark, we can place the volumetric flask on a table that is leveled, and then we can bring our eye level down to the level of the calibration mark, and then we can proceed to add the last few drops of water until the bottom of the meniscus aligns perfectly with the calibration mark. So if you observe now, the bottom of the meniscus and the calibration mark is perfectly aligned. This indicates that you have added the right amount of water to produce this 250 milliliter solution. If you by a mistake overshoot, meaning if you add little bit more water than the required amount of water, let's say just a single drop or maybe 2 drops, when you're rushing, if you add a little bit extra water, you cannot simply remove it with the use of a dropper and say that you have produced a standard solution. If you add a few drops, or if you add extra few drops of water onto this solution, then you would have diluted the solution by the amount of water that you have added extra, or additional number of drops that you have added might have diluted the solution. And if you remove those 2 drops of water that you have added additionally, you will be removing certain amount of sodium carbonate along with those drops. At that point, we cannot be sure about the number of sodium carbonate moles that are present in this solution. So therefore, we cannot be sure about the concentration of this solution. The concentration of the solution might not be very accurately 0.1 moles per decimeter cube. It might be ever so slightly different to that. So at that point, it is not a standard solution. So you will have to restart this entire process again. So that is why we take a really good care when you're adding the last few drops, because we do not want to add even a single drop additionally, making the meniscus appear slightly above the calibration mark. The meniscus and the calibration mark should perfectly align with one another. If the meniscus is slightly above the calibration mark, at that point you will have to restart this entire process from the point where we measure the sodium carbonate all the way up to addition of water. You will have to restart this process and do it one more time. So students, take precaution when you're adding the last few drops of water to produce this standard solution. After adding the last few drops, just to double check, you can bring it up to your eye level again and observe whether the meniscus is aligned with the calibration mark. And after preparing it, or after adding the right amount of water, we are still not done yet. You will have to mix this solution. To mix the solution well, you will place the stopper of our volumetric flask like so, and then we will apply some pressure and we'll close it with our finger like this, and then we will turn it upside down. We can turn it upside down a couple of times to make sure that this solution is well mixed to produce a homogeneous solution. Now, we have prepared a standard solution where the concentration of sodium carbonate is 0.1 moles per decimeters cube. We know that this concentration is accurate as we measured the sodium carbonate needed to produce this concentration very accurately, and we made sure to transfer all of the solid without any spilling onto our volumetric flask. And finally, we made sure the amount of water added was added correctly until the bottom of the meniscus of this solution aligns perfectly with the calibration mark found in our volumetric flask. Now students, this is how we prepare a standard solution. Whenever you want to prepare a solution with a known concentration, you will have to follow these steps and you will have to use this equipment to produce a solution of known concentration or solution with accurately known concentration. Let's move on to the next session where we will be discussing additional theory parts and questions revolving around this experiment. Students, we initially had a look at the theory part revolving around experiment number 4, and then we moved into the lab and conducted the experiment, and now here we are going to discuss some questions revolving around experiment number 4. So let's take a look at the first question. First question talks to us about solution B, a solution that is labeled B. So let's take a look at the question. Solution B contains sulfite and oxalate ions in an acidic medium. 25 cubic centimeters of solution B was reacted with exactly 40 cubic centimeters of 0.5 moles per decimeters cube concentrated KMnO, and all of the KMnO4 has actually completely reacted. Potassium permanganate has completely reacted with 24 cubic centimeters of the solution B. And the resultant solution was then treated with excess barium chloride, and then in the presence of nitric acid, and then obtained a white precipitate that had a mass of 0.466 grams after it was dried. And using this information, the question is asking us to calculate the concentration of sulfite ions and oxalate ions in our solution B. Now students, it will be easier if you draw a small sketch of what is happening here. We have a solution called B, and in this B solution we have sulfite ions and oxalate ions. We have both of these ions in this solution B, and we have taken 25 cubic centimeters of solution B, and we have reacted it with exactly 40 cubic centimeters of acidified KMnO4. Acidified KMnO4 with a concentration of 0.05 moles per decimeters cube. Now, after that, the resultant solution, after this is done, the resultant solution was then added with barium chloride. And when you added a barium chloride, excess barium chloride, we would see the formation of a white color precipitate. And this precipitate had a mass of 0.466 grams. Now these are the information, so this precipitate was dried and weighed, and these are the information that is given to us. So now it is asked from us to calculate the concentration of sulfite and oxalate ions. Now students, what happens to the sulfide and the oxalate when they are reacted with acidified potassium permanganate? What happens? Sulfide will turn into sulfate. Acidified potassium permanganate is an oxidizing agent. So therefore, it will get oxidized to form sulfate. And oxalate will get oxidized to form carbon dioxide. Since there are two carbons here, I will write 2CO2. So potassium permanganate will be used to oxidize both sulfite and oxalate. Sulfite will be oxidized to sulfate and oxalate will be oxidized to carbon dioxide. So for both of these processes, we will be using this acidified potassium permanganate. So the acidified potassium permanganate volume alone can't tell us the concentration of either one of these ions, because acidified potassium permanganate is used to oxidize both of these ions. Now afterwards, students, after all of the sulfite ions are turned into sulfate, after all of the oxalate is turned into carbon dioxide, we have added barium chloride to the medium. So barium chloride will introduce barium 2+ ions. So barium 2+ ions in the presence of sulfate ions will produce a precipitate. So this precipitate that is produced, the precipitate that is produced here is basically barium sulfate. Barium ions and sulfate ions together is a well-known precipitate, which is barium sulfate. So if you know through this particular piece of information, we can calculate the sulfate ions that is present in the medium, because all of the sulfate ions are precipitated out, because the question says we have added excess amount of barium chloride, meaning barium ions are in excess, they will never run out before the sulfate ions does. So therefore all of the sulfate ions are now precipitated out. So if you can calculate the sulfate ions, then you can find out the sulfite ions. And when you know the number of moles of sulfite ions, you can calculate its concentration. So if you know the number of sulfite ions that were present in the medium, then you can calculate the amount of potassium permanganate that was spent on converting sulfite into sulfate. And using this information about the concentration of potassium permanganate and the volume of potassium permanganate, we can calculate the total amount of potassium permanganate that was spent on oxidizing both sulfite and oxalate. So if you know the amount of sulfite that was present in the medium, we can calculate the number of potassium permanganate moles that was spent on oxidizing sulfite. So with that information, you can find out the number of moles of potassium permanganate that was spent on oxidizing oxalate. Using that information, we can calculate the oxalate concentration. So let's move on to actually carrying out this calculation. So we'll move on to a new slide. We'll first take barium sulfate. In this case, we will first calculate barium sulfate's molar mass. So barium is 137, sulfur is going to be 32, and there are 4 oxygens. One oxygen is 16, 16 into 4 is 64. So when you add them together, you can see 7 plus 2 is 9, 9 plus 4 is 13. You will send 1 to over here. You can see 7 plus 6 is again going to be 13. This will be 233 grams per mole. This is the molar mass This is the molar mass of barium sulfate. So after getting to the molar mass, we can move on to calculating the number of moles of barium sulfate that was present in the precipitate that we were talking about earlier. We saw there was a precipitate that was formed in the final step, and that precipitate had a mass of 0.466 grams. 0.466 grams, and this is barium sulfate. So if you know that this is barium sulfate, and if you know the mass accurately, then you can calculate the number of moles of barium sulfate that was present in the medium. Mass was 0.466 grams. Molar mass is 233 grams per mole. So if you divide this, it is going to be 2 into 10 to the power minus 3 moles. So students, this is the number of moles that is going to be present in the medium. So you may ask, how did I arrive at 2 into 10 to the power minus 3? So if you are wondering about that, I can show you the calculation. So you can write this number as 466 if you jump this decimal place 3 times to the right hand side. And as you do that, there will be a 10 to the power figure attached to it now, which is going to be 10 to the power minus 3. And then we have 233 here, grams per mole. So you can see unit wise also, grams cancel off. 233 and 466 will cancel off because there are two 233s in 466. So answer is going to be 2 into 10 to the power minus 3 moles. 2 into 10 to the power minus 3 moles. So this is the number of moles of sulfate. Because if you know that barium sulfate we have 0.002, right? 10 to the power minus 3 means 10 to the power minus 3 means 0.002. Both of them are the same, students. I hope you know this by now. So we have 0.002 moles of barium sulfate. So in each barium sulfate, we have one sulfate ion. In each barium sulfate, we have one sulfate ion. So barium sulfate to sulfate ion ratio is going to be 1:1. Meaning if you have this many moles of barium sulfate, we have this many moles of sulfate ions as well. And earlier on, we noticed that when you have sulfite ions oxidized by H plus KMnO4, potassium permanganate, acidified potassium permanganate, they turn into sulfate ions. The ratio between these are also 1:1. If you want to very clearly see it, in this reaction also, sulfite to sulfate ion ratio is 1:1. So if you know that in the entire medium there were 0.002 moles of sulfate ions, which we calculated earlier, was present, then can you find out the number of moles of sulfite ions that were present in the same medium? Yes. So sulfate ions were produced from sulfite ions. So if you have this many amount of sulfate ions in the medium. That means in solution B, 25 milliliters of solution B, they have exactly 0.02, which is 0.002 moles of sulfide ions in that 25 milliliters of solution B as well. So we can easily now calculate the concentration of sulfide ions. So if you are talking about the concentration of SO3 2 minus sulfide ions in solution B is going to be number of moles divided by volume. So number of moles is 0.002 moles divided by the volume, which is going to be 25 cubic centimeters. So 25 cubic centimeters can be converted into cubic decimeters by dividing by 1000 or multiplying it with 10 to the power minus 3. 10 to the power minus 3. So this is 25 cubic centimeters written as decimeters cube. You can write this as a division as well, 25 divided by 1000, or else 25 multiplied by 10 to the power minus 3 is also correct. So at this point, if you want, you can rewrite this 0.002 as 2 into 10 to the power minus 3. Now 0.002 can be written like this as well. And then we have 25 into 10 to the power minus 3. You can see 10 to the power minus 3, 10 to the power minus 3 cancels off, leaving us with 2 over 25. So when you solve this, the answer is going to be 0.08 moles per decimeters cube. Units are important, students. Please make sure that you use the correct units at the end of each calculation. So 2 divided by 25, 0.08. So now we have calculated the concentration of concentration of sulfide ion in solution B. So in solution B, the concentration of sulfide ions is this, and the number of sulfide ions in solution B was also calculated, which is this 0.002 moles. So if you know that, we can actually move on to calculating the oxalate ion concentration. But before we move on to calculating the oxalate ion concentration, we need to first calculate the amount of potassium permanganate that was actually spent on sulfite ions to convert it into sulfate ions, because potassium permanganate was spent for both sulfite and oxalate ions. So over here, we will have the total KMNO4 used is going to be equal to concentration multiplied by volume. So concentration was 0.05 moles per decimeters cube. We can confirm that over here the concentration of this solution is given here. You can see concentration of potassium permanganate is 0.05 moles per decimeters cube, and then we have used 40 milliliters or 40 cubic centimeters of the solution. So cubic centimeters should be converted into decimeters cube. That can be done by multiplying with 10 to the power minus 3 or by dividing 40 by 1000. And this is going to be now in decimeters cube. Right. So we can see decimeters cube over here, decimeters cube, and per decimeters cube cancel off, leaving behind the only unit MOL, and we have 0.05 multiplied by 40, and then there's a 10 to the power figure as well, don't forget. Now we have 40.0 multiplied by 0.05. So when this multiplication is solved, it's going to be 2.0 into 10 to the power. We have a 10 to the power figure here, 10 to the power minus 3. 2.0 into 10 to the power minus 3. Okay, so this is the number of moles. This is the number of moles of potassium permanganate, or in other words, we can write 0.002 moles. Both of these forms are correct. So this is the number of moles of potassium permanganate that was used to oxidize both oxalate and sulfite. So we know the number of moles of sulfite that was there in the medium. So in order to calculate the number of moles of potassium permanganate spent on that amount of sulfite, we have to write the balanced equation for this reaction. So the balanced chemical equation for the reaction would be written like this. So we have two half reactions. We have sulfite, SO3 2 minus, turning into SO4 2 minus, and this is happening in acidic medium. We have one oxygen over here that is additional on the right hand side. So to balance that off, we can add a water molecule here. So when a water molecule is added, we can see the number of hydrogens is not going to be balanced. We can add two H pluses onto the right hand side. So now the H pluses are balanced, or hydrogens are balanced rather. Only thing that is not balanced would be charge. Sulfur is balanced, oxygen is balanced, hydrogens are balanced. The charge is not balanced. You can see over here, overall charge on the left hand side of the arrow is -2. Overall charge of the right hand side of the arrow is 0. So to bring the overall charge to -2, we can add 2 electrons. So this is our equation number 1. And the equation number 2 would be our permanganate ions, MnO4 minus ions, turn into Mn2 plus. In the acidic medium, MnO4 minus turns into Mn2 plus. We can see there are 4 oxygens on the left hand side. So we have to add 4 water molecules to get just 4 oxygens on the right hand side. So usually, students, when we are balancing equations acidic medium, if you have 4 oxygens over here and you don't have any oxygens here, to balance off those 4 oxygens, you can add 4 water molecules to the other side, because each water molecule brings in 1 oxygen. But when you do this, the number of hydrogens on the left hand side is not going to be balanced, because we have now introduced 8 hydrogens onto the right hand side. So the left hand side is now not having any H hydrogens here. So since this is happening in the acidic medium, there are enough and more H pluses, so we can add H pluses over here, 8 H plus. So now the hydrogens are balanced. But then again, you can see although all the atoms are balanced, the charges are not balanced. On the right hand side, the overall charge is +2. On the left hand side, we have +8 and 1 minus, meaning the overall charge is +7. So we need to bring this +7 charge to a +2 charge, because we can't add hydrogens to the right hand side to increase the positive charge there, because if you add hydrogens, then the hydrogen balance will again go off. So you can have the option of adding electrons. So if you add 5 electrons to this side, electrons carry negative charge, so overall charge on the left hand side also is going to be 2 plus, and the overall charge of the right hand side will also be 2 plus. So now this is completely balanced. So this is going to be our reaction 2. Now, when it comes to these types of equations, you need to have the same number of electrons that are released and taken up by the two different reactions. So the first reaction gives off 2 electrons, but the second reaction takes up 5 electrons. So this number of electrons that are released and number of electrons that are taken in by the second reaction are not the same. So we'll have to multiply 1 by 5 and 2 by the second reaction by 2 to get those two electrons to be the same. Reaction number 1 is going to be multiplied by 5. Reaction number 2 is going to be multiplied by 2. And we will be adding them together afterwards. So we will directly do that. So we have water here. Water multiplied by 5, you have 5 water, H2O. And we have 5 SO3, 2 minus. I will multiply this by 2. We have 16 H pluses. And when you multiply MnO4 minus by 2, it's going to be 2 MnO4 minuses. And then on the right hand side of the equation, we have 5 sulfate ions, 10 H plus ions, and we have 2 Mn2 plus ions, and 8 water molecules. Now you can see there are certain chemical species that are present on both sides, such as we have water on both sides and we have H pluses on both sides, so we can cancel them off. So let's cancel them off. 8 water over here and 5 water over here will cancel off, and we have 3 water molecules remaining here. We have H pluses, 10 H pluses here and 16 H pluses here, resulting in only 6 H pluses remaining here, because there were 10 there, 10 and 16. When we cancel them off, 6 will remain here. So the final equation that you obtain after cancelling off the chemical species that are present on both sides is going to be 2 MnO4 minus plus 6 H plus plus 5 SO3 is going to be turning into 5 SO4, 2 minus, 2 Mn2 plus, and 3 H2O. Now before we move any further, you can quickly see if this is completely balanced. We have 5 sulfurs, 5 sulfur here, 2 Mn on the right hand side as well. We have 6 H pluses on the left hand side, and we have 6 hydrogens on the right hand side as well. On the left hand side there are 6 H pluses. On the right hand side there are 6 hydrogens as well. Overall number of oxygens on the left hand side is, we have 8 here, 8 plus 15. right? 8 plus 15 is going to be altogether 23. And over here we have 20. 5 into 4 is 20 oxygens. 20 plus 3 is going to be 23. So therefore number of oxygens are also balanced, students. So this is the balanced ionic equation for the oxidation of sulfite ions into sulfate ions. The only reason why we wrote this equation is because we want to figure out the ratio between MnO4 minus ions and sulfite ions, because we need to figure out how much of potassium permanganate was getting used up to convert 0.002 millimoles of sulfite ions that was present in the medium. Now we calculated earlier the number of sulfite ions in the medium over here. Number of sulfite ions in the medium we calculated to be 0.002 moles. So to react with that 0.002 moles of sulfite ions, we need to figure out how many potassium permanganate was used up. And to calculate that, we need the reaction ratio, or the ratio between potassium permanganate to sulfite ions. So permanganate ions, we have 2. Over here we can see 2:5 is the ratio. 2:5 is the ratio. So we have 0.002 moles of sulfite ions. So how many moles of potassium permanganate is needed? You can calculate it by doing this: 0.002 divided by 5 multiplied by 2, divided by 5 multiplied by 2. So in other words, I can write KMnO4 spent on SO3 2 minus ions is going to be equal to 0.002 moles divided by 5 multiplied by 2. So I can write it like this. So the answer would be, at that point, we have 0.004 divided by 5, which is going to be 0.008. 0.008 moles. 0.0008 moles. 0.0008 moles of potassium permanganate was used up to react with our sulfite ions. After calculating this number of moles, since we know the total number of potassium permanganate that was used for this experiment, we can calculate the number of moles of potassium permanganate that was spent on converting oxalate ions into carbon dioxide. So I can now write the KMnO4 moles spent on C2O4 2 minus ions. That will be total KMnO4 moles minus the KMnO4 spent on SO3 2 minus. So students, the total number of potassium permanganate ions we calculated earlier, or if not, we can actually calculate here again. So students, the total number of potassium permanganate can easily be calculated here itself. The concentration is 0.05 moles into 40 multiplied by 10 to the power minus 3. We calculated this earlier as well. And then we have the KMnO4 spent on sulfite ions, which happens to be 0.0008 moles. So this number is 0.002 moles. 0.002 moles minus 0.0008 mole, which results in 0.0012 moles. So this is the number of moles that were actually spent on converting the acidified, that was spent on converting oxalate ions into carbon dioxide. Once you get to that value, it is now time for us to calculate the oxalate ion concentration. And in order to calculate the oxalate ion concentration, we need to know the equation. C2O4, 2 minus, turned into CO2. So since there are 2 carbons here, there will be 2 carbons here as well. And to balance the electrons, we will have to put 2 electrons, or we have to add 2 electrons to the right hand side. And KMnO4 balancing we have done earlier as well. MnO4 minus will turn into Mn2 plus. And since we have done this earlier on, I will directly write it for H2O here. To balance the hydrogens, we will add 8 H pluses here. And then to balance the charges, we'll add 5 electrons here. So this is reaction number 1. This is reaction number 2. Again, the number of electrons released, number of electrons taken in do not balance. So therefore, we will add them together by multiplying them with relevant numbers. The first reaction should be multiplied by 5, and then to it we'll add the second reaction multiplied by 2. At that point, we will have 5. At that point, we will have 5 C2O4 and we have some H pluses and MnO4 minuses here. So this is multiplied by 2. So we have 16 H pluses and 2 MnO4 minus, turning into 10 CO2, and we have 2 Mn plus, 2 Mn2 plus, along with 8 water molecules. So on both sides, do we have any similar chemical species on both sides? Actually, at this point, we don't have any similar chemical species on both sides. So this is the balanced ionic equation. We don't have to cancel off anything. But if you want to see if it is balanced, you can see there are 10 carbons, 16 hydrogens, 16 hydrogens. And we have 2 Mn and 2 Mn here. Number of oxygens, if you calculate, you can see in MnO4 minus, there's going to be 4 oxygens in each. So therefore, since there are 2 permanganate ions, there are 8 oxygens there. And in oxalate ions, there are 20 oxygens. So 8 plus 20 is going to be 28. So 10 multiplied by 2 over here is 20. 20 plus 8 oxygens, 28. So it is completely balanced. So what is the ratio between K or MnO4 minus? What is the ratio between MnO4 minus ions and C2O4 2 minus ions? The ratio between the two is 2 is to 5. 2 is to 5. You can see after solving this equation or balancing this equation, we can see the ratio between the two is 2 is to 5. So we know the number of moles of permanganate ions that were spent on oxalate. We will use a different color for this. So we know the number of moles of permanganate ions that were spent on oxalate is 0.0012. So we need to figure out how many oxalate ions were actually present in this medium. So in order to calculate that, we can write this sentence. Number of C2O4 2 minus moles in the medium is equal to 0.0012 moles divided by 2 multiplied by 5. Divided by 2 multiplied by 5. So 0.0006 into 5 moles, which is going to be 0.003 moles. So at this point, we know the number of moles of oxalate ions that were found in 25 milliliters of solution B. So if you know the number of moles that is present of oxalate in solution B, we can calculate the concentration. Concentration of C2O4 2 minus in solution B is equal to number of moles divided by volume. Number of moles is 0.003 divided by 25 milliliters. Don't forget that in the original solution B, we worked with 25 milliliters. So these oxalate ions were present in those 25 milliliters. The volume is 25 milliliters. We have to convert it into decimeters cube. You have to multiply it by 10 to the power 3, 10 to the minus 3 decimeters cube. If you want, now when you're doing calculations, you do not have to rewrite this. If you can work it out in your head, you can do that. But in order to show you, I can rewrite this in a different manner so that you can very easily work it out. But keep in mind, students, you don't have to rewrite it like this to get to the answer. If you can work it out in your head, you should do that without having to write it down. So these 10 to the power minus 3 figures will cancel off, leaving us with 3 over 25. So instead of solving 3 over 25, we can directly multiply both sides with 4, both the numerator and denominator by 4. The reason why we choose 4 is because when you do that, 25 becomes 100. So it is easier to keep the final answer, because when you divide by any number by 100, you have to know that you jump the decimal place twice to the left hand side. So what you get here is 3 divided by 25. If you multiply both by 4, for example, if I do this, right, you can again do this in your without having to write it down on a piece of paper you should be able to work it out in your mind. And when this happens, it gets to 12 divided by 4. So 12 divided by 100. 12 divided by 100 is basically equal to 0.12. This is moles per decimeters cube. Now you don't need to show this working. The only reason why I showed it to you is just to make sure that you understood what I meant by multiplying both the numerator and the denominator by 4, because it will make your life easier. When you do a multiplication, when you carry out a multiplication for both the numerator and the denominator using the same value, there's no change in the value of this particular fraction, so therefore there's no harm done here. But you don't have to show this working. This working is not required. So finally you get to this answer, which is 0.21 moles per decimeters cube. This is the concentration of oxalate ions in the medium. So students, now this was a very interesting question. So this is the oxalate ion concentration, and we calculate the concentration of sulfite ions, which is 0.08, and then over here we can write them down for clarity. So the concentration of oxalate ions and the concentration of sulfite ions, SO3, to minus concentration was 0.08 moles per decimeters cube in this 25 milliliter, actually in the original solution B. And when you're finding the concentration, we used the volume of 25 milliliters because we originally took only 25 milliliters out. But that 25 milliliters also had the same concentration as the original solution. So we can say the sulfate ion concentration of solution B happens to be 0.08 moles per decimeters cube, and oxalate ion concentration happens to be 0.12 moles per decimeters cube. Alright students, this brings us to the end of question number 1. This is the end of question number 1. So let's move on to question number 2, which is also a very interesting question, 2008 A-level question. The density of an aqueous solution made using pure sodium carbonate is 1.0212 grams per cubic centimeter. Calculate the concentration of this solution. Assume that the water density given temperature is, at the given temperature, is 1 gram per decimeters cube, and no change of volume during the dissolution of sodium carbonate. So we have a sodium carbonate solution, and the density of this sodium carbonate solution is 1.0212 grams. And this is basically a sodium carbonate solution. Okay, so students, now they're asking you, what is the concentration? What is the concentration of the solution? To tackle this question, we will use 1 decimeters cube of this solution, and we will see the concentration of sodium carbonate that is found in this solution. So the water's density, they say the water's density is 1 gram per cubic centimeter. You should keep in mind. So students, if you take, let's say, 1 decimeters cube of water, what will be the mass of this 1 decimeters cube volume of water? Now they have given, when it comes to water, they have given the density of water is 1.00 grams per cubic centimeter, or in other words, if you take 1000 cubic centimeters, the weight will be 1000 grams. So, you know 1 decimeters cube is equal to 1000 cubic centimeters. So what we have here is 1000 cubic centimeters, what we have taken here. 1 cubic centimeter, now decimeter, the density that we have here communicates to us 1 cubic centimeter has a mass of 1 gram. Meaning, if you took 1000 cubic centimeters, that would have a mass of 1000 grams. So over here we have 1 decimeters cube, which is 1000 cubic centimeters. So therefore this has mass of 1000 grams. Now imagine we dissolve sodium carbonate in this. We dissolved certain mass of sodium carbonate. We'll say M amount of NaCO3 was dissolved in it, and then we prepared a new solution now. But in this question they say when you're dissolving sodium carbonate, volume didn't change. That's a very important piece of information. They say in this question, when you prepare the solution, volume did not change. Meaning, whatever the mass of sodium carbonate that we added to 1 decimeters cube of water dissolved in it, or the sodium carbonate dissolved in 1 decimeters cube of water, but it did not result in increasing the volume of the solution. The volume of the solution remained at 1 decimeters cube. So we have now a 1 decimeters cube of our solution. This is our Na2CO3 solution, not just NaCO3, keep it in mind. So this is sodium carbonate solution we have here, and the density of sodium carbonate was given. So they said density of the sodium carbonate solution was given. Density of the sodium carbonate solution was given as 1.0212 grams per centimeters cube. So what does that mean? That means in this solution, if you take 1 centimeters cube is going to have a mass of 1.0212 grams. Now we have 1 decimeters cube. 1 decimeters cube of the solution is equivalent to 1000 grams, or 1000 cubic centimeters, not grams, of the solution. 1 decimeters cube is equal to 1000 cubic centimeters. So 1 cubic centimeter has a mass of this. Then what is the mass of 1000 cubic centimeters of the solution? It's going to be 1021.2 grams. So if you don't like to use so many lines to get to this answer, you can use the calculation as well, students, which is density of a given solution is equal to mass of the solution divided by the volume of the solution. So in this case, we know the density, we know the volume. If you want to get to the mass, because since we know the density and the volume, we can easily find out the mass. So the mass is going to be equal to density multiplied by volume. So what is the density? Density is 1.0212 grams per cubic centimeter. So the density unit is in cubic centimeters, or per cubic centimeters. So volume should also be substituted in cubic centimeters, otherwise the calculation would not work. So we have taken 1 decimeters cube, we have to convert it into centimeters cube. 1 decimeters cube is equal to 1000 centimeters cube. So you can see centimeters cube cancel off. We have this number multiplied by 1000, which results in 1021.2 grams. This is the mass of the sodium carbonate solution that we have prepared here. So this has a mass of 1021.2 grams. So what is the difference? What is the difference between these two solutions? What did we do when preparing this sodium carbonate solution? We took 1 decimeters cube of water and we prepared 1 decimeters cube of sodium carbonate solution. So what did we do to prepare sodium carbonate solution? We added sodium carbonate. So the weight difference or the mass difference between these two situations came from the sodium carbonate that was dissolved. So therefore, students, we can calculate the mass of sodium carbonate in 1 decimeters cube of solution. Is equal to 1021.2 grams minus 1000 grams. The mass of the sodium carbonate solution minus the mass of water. When that happens, we get to the answer 21.2 grams. 21.2 grams. So this is the mass of sodium carbonate present in 1000 cubic centimeters of water, or this is the mass of sodium carbonate present in 1 decimeters cube solution of sodium carbonate. So if you know the mass of sodium carbonate there, you can actually now calculate the final concentration of this solution. So you can write number of moles of sodium carbonate is equal to mass divided by molar mass. So mass is known to us 21.2 grams. So sodium carbonate molar mass, we can calculate the sodium carbonate molar mass, Na2CO3. Sodium has a mass of 23, so we have 2 sodiums, so that is going to be 23 into 2, which is 46, and we have 1 carbon which has a mass of 12, and we have 3 oxygens. 1 oxygen is 16 into 3 is 48, right? So we have 48 plus 12, which is 60, 60 plus 46, which is going to be 106. Is going to be 106. So what is the molar mass of sodium carbonate? 106 grams per mole. This is the molar mass of sodium carbonate. So if you bring it over here, 106 grams per mole, you can see grams cancel off, and over here the answer would be, if you can see over here, this looks at 212, but there's a decimal place over here. You can write it like this also. If you are finding it difficult to solve a question just by looking at it, you can write it like this. Still, the value is the same. So you can see 106 and 212 will cancel off. There are 206s in 212. So the answer at that point is going to be 2 into 10 to the power minus 1, which is basically 0.2 moles. So there are 0.2 moles in 1 decimeters cube of the solution. So what is the concentration of sodium carbonate? We can write concentration of sodium carbonate is equal to number of moles, which is 0.2 moles, divided by volume, which is going to be 1 decimeters cube, which happens to be 0.2 moles per decimeters cube. So students, this is how you would calculate the concentration of sodium carbonate in this solution. I hope this was clear to you, and all that we did, if you're going through it, we initially wrote down that there is 1 decimeters cube of water. We took 1 decimeters cube because it is easy to work with when it comes to this type of calculation, because concentration is anyway kept to 1 decimeters cube, right? For example, the unit of concentration is moles per decimeters cube. So using 1 decimeters cube will make it easier for us to calculate the number of moles of sodium carbonate that is present in 1 decimeters cube worth of sodium carbonate solution. And using the density values, we realize there's 21.2 grams of sodium carbonate dissolved in 1 decimeters cube of water. And using that, we calculated the concentration of sodium carbonate in this solution. So that is how you would find out the concentration of a solution if the density is given to you, along with the knowledge that when you are dissolving the sodium carbonate in a specific volume of water, if the assumption is taken that we are not changing the volume as we dissolve sodium carbonate, you can easily calculate the concentration using the method that we did. So now let's move on to the next question. Now we have the third question here. Solution Y contains both diluted sulfuric and oxalic acid. 25 cubic centimeters of this solution was titrated with 0.05 moles per decimeters cube concentrated potassium permanganate solution. The required volume of KMnO4 was 24 cubic centimeters. After completing the initial titration, the resultant solution was subsequently titrated with 0.04 moles per decimeters cube concentrated sodium hydroxide solution. The required volume of sodium hydroxide was 15 cubic centimeters. So what are they saying here? That there was a solution Y that had both sulfuric acid and oxalic acid, 2 acids together. And we then reacted with acidified potassium permanganate, and the amount of acidified potassium permanganate actually required to titrate 25 cubic centimeters of this solution was given here, 24 cubic centimeters. So out of these two chemical species, we have sulfuric and oxalic acid. Which one can get oxidized? Can the sulfate ions in sulfuric acid get further oxidized? Can it get further oxidized? The answer would be no, it can't get further oxidized. What about oxalic acid? Oxalic acid has H pluses and C2O4 ion, right? Oxalate ion. So the oxalate ion can get oxidized. Oxalate ion can get oxidized to CO2. So only thing that can get oxidized over here between these two chemical species or these two acids is going to be oxalate ion, or the oxalic acid produce carbon dioxide. When oxalate ion is oxidized, it will produce carbon dioxide. So this amount of potassium permanganate was spent on oxidizing oxalate ion. After the oxalate ion is completely oxidized, we will be titrating the remaining amount of acid with sodium hydroxide. So when I say the remaining amount of acid, we are not only talking about this. Keep in mind, oxalic acid also had some H pluses released, but some of the H pluses were reacted to carry out this oxidation reaction. As you know, potassium permanganate, when it is carrying out its oxidation reaction, usually uses up H plus ions. Majority of the time, the H plus ions that are produced only by the oxalic acid is not going to be sufficient enough. Some H pluses from the sulfuric will also be taken. So the remaining amount of H pluses is usually found out easily by the sodium hydroxide titration, but that does not indicate that the amount of H pluses over here is going to correctly represent the number of sulfuric acid molecules that are or that were present in the medium, right? So some of the H pluses from sulfuric would have gotten used up in the first step of this reaction where the oxidation took place, because as potassium permanganate oxidizes oxalate, it will use up some H pluses, and the H pluses provided by oxalic acid is not going to be enough. You would see this when we write the balanced chemical equations. So that means some H pluses from sulfuric will also be used. And when in the second step, when you are titrating the H pluses in the medium using sodium hydroxide, the titration will not correctly represent the number of H pluses that came into the medium by sulfuric acid, because some of the H pluses of sulfuric would have gotten used up in the first place on the first step as well. So the first question that we get over here is write the balanced equations for the reaction. Then the second one is determine the concentration of the following solution, oxalic acid and sulfuric acid. So now they're asking us to write, we'll take the first question. They're asking us to write the balanced chemical equations for this reaction. We have two reactions that are happening here. Mainly, you can see acidified potassium permanganate reacting with oxalate ion. So the reaction number 1. We have C2O4, 2 minus ions turning into CO2. Now you can use the ionic equation, or you can directly use the balanced chemical equation. So if you prefer to use balanced chemical equation, you can do that. Instead of taking the ion, we can take, instead of taking the ion at that point, we can take the acid, which is H2CO3, so H2C2O4, and then we have over here 2 H pluses. So when one oxalic acid gets oxidized, it will produce 2 carbon dioxide and 2 H pluses. And over here on the left hand side, the overall charge is 0. To make the overall charge 0 here, you will have to write 2 electrons here. At that point, this is going to be the first half equation. And then we can write the second half equation using potassium permanganate. So we have permanganate ions, MnO4. We can write KMnO4 turning into Mn2 plus ions. Along with, we'll have obviously potassium plus ions. And when you write this equation like this, you can see very clearly the oxygen is not balanced. So to balance off the oxygens, we will add 4 water molecules here, 4 H2O, right? So we have 4 H2O on the right hand side. And since we have now introduced hydrogen into the mix, we have to balance hydrogen as well. Hydrogen comes from H plus, so we can write there are 8 hydrogens. Since this is happening in the acidic medium, we can write 8 H pluses. And then we can proceed to balancing this equation. We can see now on the right hand side, the overall charge is plus 3 on the left hand side the overall charge is plus 8. To balance this, you would need to add 5 electrons. So when you add 5 electrons, you can see the overall charge on both sides is balanced. 5 negative charges and 8 positive charges will bring in 3 plus on the left hand side. Right hand side also there is a 3 plus charge. Again, now in this situation also you can very clearly see, if you take a look at the number of electrons released in the first reaction and the number of electrons taken in by the second reaction, they are not the same. So to make sure that they are the same, we can multiply the first reaction by 5, and then to it we can add the second reaction multiplied by 2. So if you do that, we get to this final equation, which is 5 H2C2O3 H2C2O4 plus we have 8 H pluses multiplied by 2 is going to be 16 H pluses multiplied by 2 over here is going to be 2 KMnO4 electrons are cancelled off, so I wouldn't write that. We have 10 carbon dioxide along with 10 H pluses over here, and then we have 2 Mn2 pluses and 2 K pluses, 8 water molecules. So again, in this situation also, on both sides we have somewhat similar chemical species. On the right hand side and on the left hand side we have similar chemical species, so therefore we can proceed to cancel them off. You can see on the right hand side we have 10 H pluses here, and on the left hand side also there are some H pluses here. So let's cancel them off. 10 H pluses, 16 H pluses, leaving behind 6 H pluses here. So where does this 6 H pluses come from? These 6 H pluses, where do they come from? Do they come from the oxalic acid? No, all of the oxalic acid reacts with this, and H pluses attached to the oxalic acid is going to be present here. So these H pluses didn't come from oxalic acid. So from where did they come from? They came from sulfuric. So we can write the final equation like this. We'll use black for this. So we have 5 H2CO2O4 oxalic acid reacting with, now to get 6 H pluses from sulfuric you would need 3 sulfurics. And then we have 2 KMnO4 producing 10 carbon dioxide along with 2 Mn2 plus. So to Mn2 plus, what anion can we couple with Mn2 plus? So we brought in sulfuric acid here. So sulfuric acid brings in 3 sulfate anions. So out of the 3, 2 sulfate ions can be given to Mn2 plus. There are 2 Mn2 pluses. So we have given 2 sulfates here. Now we have produced MnSO4. And then we have 2 K pluses. The remaining sulfate ion can be given to the 2 K pluses, producing K2 SO4, right, potassium sulfate. Finally, 8H2O. We can double check whether this is properly balanced as well. You can see we have altogether, we'll take a look at the main chemical species. Carbon, there are 10 carbons here. There are 3 sulfate groups here. We have 2 Mn here. If you take a look at the other chemical species or other atoms as well, you will see all of the other atoms are also completely balanced. Okay, so with that in mind, we can now move on to the next part. So after calculating this, now this was done mainly to observe, actually this is one of the answers that we need to provide, but at the same time we can very clearly observe this. We can very clearly observe this, which is when our oxalic acid reacts, there is going to be a certain amount of sulfuric that reacts along with it. Actually, H pluses from sulfuric will be taken up for this reaction. So with each of these oxalic acid, with 5 oxalic acids, 3 sulfuric acids will also react to convert this oxalic or oxalate ion to carbon dioxide. So in the first step itself, 3 sulfuric acids were getting used up. Okay, so this is the first reaction, or the reaction that is happening in the first step of this question. And then we have the second part of this question. Let's move on to that. The second part of this question is asking us, so we can actually answer the second part here. Second part can be answered, bear with me a second. Second part can be answered here. Second part says that after we have reacted, bear with me a second. So after we have reacted 25 cubic centimeters of solution Y with acidified potassium permanganate, we are going to be titrating it with sodium hydroxide. So what happens in sodium hydroxide? When sodium hydroxide is added to the medium, sodium hydroxide will react with the remaining amount of acid, right? So the second reaction would be the remaining amount of sulfuric acid will react with sodium hydroxide. It's a very simple reaction. This equation is going to be producing sodium sulfate, salt, and water. Sodium sulfate and water will be produced here. This is the second part. This is the second equation that you should write as the answer to the first part of this question. Alright students, so now we observed what is happening in the first step and in the second step. We have this part of the question where they ask us to determine the concentration of the following in the Y solution: oxalic acid solution and sulfuric acid solution. So students, over here, to calculate the oxalic acid or the sulfuric acid solution, we have to first take a look at the first step of this reaction. The first step says we have taken 25 cubic centimeter of the solution Y and titrated it with potassium permanganate solution with this concentration, and the amount of potassium permanganate that was spent was 24 cubic centimeters. So we will note it down. It will be easier for us that way. So we have 25 cubic centimeters of our solution Y. Now solution Y contains both sulfate ions, which are not going to be undergoing any oxidation, and oxalate ions, C2O4 2 minus ions. Oxalate ions, of course, can undergo oxidation. So solution Y contains both of them. And then we are going to titrate it against potassium permanganate, right? So when you titrate it against potassium permanganate, the resultant solution is going to have carbon dioxide. Actually, carbon dioxide will be emitted. Okay, and we will have certain amount of sulfuric acid remaining here. When we wrote here that there is these two ions, we can actually write that there are two main acids. One is sulfuric acid, the other one is oxalic acid. So solution Y basically contains two things. One is sulfuric acid, the other is oxalic acid. Both of them are there in solution Y. However, when we oxidize this oxalic acid, some amount of sulfuric acid will also be used up in the acidification of this process. As you know, potassium permanganate reacts in acidic medium. So we saw earlier also when we were writing balanced chemical equation, we very clearly saw here that as oxalic acid undergoes oxidation to produce carbon dioxide, a small amount of sulfuric acid was also used up. So in this medium, we are going to have a small amount of sulfuric acid remaining, but that will not reflect the original number of moles of sulfuric acid that was present in this 25 aliquot of the solution. So we can say this is the remaining. We can say that this is the remaining sulfuric acid. And we can say after the titration, in the resultant solution, there's going to be a certain amount of sulfuric acid, but that is not the total amount of sulfuric acid that was present in the beginning of this reaction. This is the remaining amount of sulfuric acid, because some amount of sulfuric acid got used up when it comes to oxidation of oxalate ion. So then we have to calculate the remaining amount of sulfuric acid first and get it out of the way. That will be easier. So we can write over here the remaining amount of before we move on to remaining, we actually know the reaction that is taking place. We know sodium hydroxide will react with sulfuric acid. This is the remaining sulfuric acid and will produce sodium sulfate. We wrote this equation earlier, but it is easier to have it in this window as well. So we have this reaction happening. You can see the reaction ratio or ratio between sulfuric to sodium hydroxide is 2:1. 2:1. After figuring out that sodium hydroxide and sulfuric acid reacts in this 2:1 ratio, if you know the number of moles of sodium hydroxide that was spent in this reaction, you can find out the sulfuric acid that was remaining in the solution. So we can write the number of sodium hydroxide spent, NaOH spent, is going to be equal to concentration multiplied by volume. Concentration is 0.04 moles per decimeters cube. If you are not sure about that, you can actually go and check the concentration that is given in this question. So keep in mind, students, so this is a typo. This is MOL, moles per decimeters cube. So 0.04 moles per decimeters cube is the concentration. And then we have the volume. volume that was spent again was 15 cubic centimeters of volume was spent. So 15 cubic centimeters should be converted into decimeters cube. When you do that, you multiply it with 10 to the power minus 3. So we can see decimeters cube per decimeters cube cancel off, and we have to multiply 15 with 0.04. So when you multiply 4 by 15, how much is it? If you multiply 4 by 15, it's going to be 60. But this is not 4, this is 0.04. That means the answer, the decimal place should jump twice to the left again. So the answer would be 0.60 into 10 to the power minus 3 into 10 to the power minus 3. The unit is going to be mol. So this is the amount of sodium hydroxide that was spent over here. So the ratio between sodium hydroxide to sulfuric acid we saw earlier. Sodium hydroxide to sulfuric acid ratio was 2:1. 2:1. So to react with 1 sulfuric, we will be spending 2 sodium hydroxide. So we can write the remaining sulfuric acid is equal to 0.6 into 10 to the power minus 3 multiplied by, we have to actually divide by 2, which is going to be 0.3 into 10 to the power minus 3 millimoles. Or in other words, 3 into 10 to the power minus 4 millimoles. Now students, we have found out the number of moles of sulfuric acid that is remaining in this solution Y that we took. So after the first step, in the 25 original solution Y sample that we took, the remaining amount of H2SO4, the remaining sulfuric acid number of moles is going to be 3 into 10 to the power minus 4 moles. 10 to the power minus 4 moles. Alright, so this is the remaining number of moles. We now need to find out the number of moles that were actually used up in the first step. So now we are going to be considering the first reaction. Considering the first reaction. In the first reaction, we saw that potassium permanganate was reacting with oxalate, and some of the sulfuric acid was also used up. So to calculate the number of sulfuric acid that is used up, we need to find out the ratio between potassium permanganate, and since we know the number of moles of potassium permanganate used, we can easily calculate the number of sulfuric acid molecules that were used up in the first step. So again, we'll quickly, before we get to the ratio, we can write down in the first step the KMNO4 that was used for the titration, or KMNO4 that was spent. We have concentration multiplied by volume. Concentration is 0.05 moles per decimeters cube, and the volume was 24 centimeters cube. So we have to multiply it by 10 to the power minus 3. So then you convert it to decimeters cube. So let's double check these values. Let's double check the values. You can see this concentration of potassium permanganate was 0.05 and the volume was 25 or 24 cubic centimeters. All right. So now you can see that decimeters cube per decimeters cube cancel off. The final answer is going to be in moles. So we have 24 multiplied by 5. You can actually rewrite this as this: 5 multiplied by 10 to the power minus 2 multiplied by 24 10 to the power minus 3. If it is easier for you to work with it like this, it is okay for you to go ahead and rewrite it in a manner that is easier for you to work with. So if you multiply 5 by 24, it's going to be 120. Then we have 10 to the power minus 2 here, multiplied by 10 to the power minus 3. So instead of writing it like this, we can directly write it in the following way, which is 1.2 into 10 to the power minus 3 moles. So this is the number of moles of potassium permanganate that was used. 1.2 into 10 to the power minus 3 millimoles. This number of moles that was used. And then if you know the number of moles of potassium permanganate, and if you happen to know the ratio between potassium permanganate and sulfuric acid in the first reaction, then you can calculate the number of sulfuric acid that was used up in the first reaction. So let's move on to the balanced chemical equation of the first reaction. This is the balanced chemical equation of the first reaction. We can see when you used up 2KMnO4, along with it, we used up 3 sulfuric acid as well. With 2KMnO4, 3 sulfuric acid was used up. This is the balanced chemical equation we wrote in the first part of this particular question. So the answer would be, along with 2 KMnO4, 3 sulfuric acid molecules were used. That means we can calculate the sulfuric acid moles that were used in the first step. That is going to be equal to KMnO4 spent, KMnO4 moles spent, KMnO4 moles spent multiplied by, we have 3 divided by 2. KMnO4 moles spent multiplied by 3 divided by 2. 1.2 into 10 to the power minus 3 moles of potassium permanganate was spent. This many moles of KMnO4 was spent. Then at that point, if you carry out this multiplication, you can see that we are getting to, when you divide 1.2 by 2, it's going to be 0.6. 0.6 multiplied by 3 is going to be 1.8 into 10 to the power minus 3 millimoles. This many moles of sulfuric acid was spent in the first reaction. in the first reaction, this many moles of sulfuric acid was spent. And then we earlier calculated the remaining amount of sulfuric acid. So what is the overall number of sulfuric acid? So we can write that here. Total moles of sulfuric acid is basically the sulfuric acid spent in the first step, 1.8 into 10 to the power minus 3 plus the remaining amount of sulfuric acid, which was 3 into 10 to the power minus 4. Now this value is in 10 to the power minus 3. So we can convert this into a 10 to the power minus 3 value as well by writing it like this, 10 to the power minus 3. Right, so we can keep it like this. So when you bring that value over here, these are all moles. So you can see we have 10 to the power, similar 10 to the power minus 3 values here. So it's going to be 1.8 plus 0.3 into 10 to the power minus 3 millimoles, resulting in the final answer, which is going to be 2.1 into 10 to the power minus 3 moles, or in other words, 0.0021 moles. So this is the number of moles that was present in the original sample, which means the concentration of sulfuric acid in solution Y can be calculated. Number of moles divided by volume. Number of moles happens to be 2.1 into 10 to the power minus 3 moles divided by 25 into 10 to the power minus 3 decimeters cube. Which will bring the value to, you cancel this off, and when you solve this, it's going to be 8.4, actually 0.084 moles per decimeters cube. This is the concentration of our sulfuric acid in solution Y. So students, the calculation of sulfuric acid in solution Y can be done like this, and when you're carrying it out, please make sure to keep in mind that sulfuric acid is getting used up in the first step as well. And then in the second step, when you're titrating the sulfuric acid, only a small amount of sulfuric acid is present in the medium. So that is the remaining amount of sulfuric acid after some amount of sulfuric acid is used up in the first step. I hope you are clear with that. Now we can move on to the next step. Students, although we initially calculated the sulfuric acid concentration in solution Y, we actually didn't calculate the oxalic acid concentration of solution Y, which is the easier one to calculate because when it comes to oxalic acid, we need to first of all know the oxalic acid to KMnO4 ratio, which we found out earlier in this reaction. You can see over here the oxalic acid to KMnO4 ratio is very clearly known. 2 KMnO4 would react with 5 oxalic acid. So oxalic acid to KMnO4 ratio is going to be 5 to 2. 5 is to 2. So 5 oxalic acid will react with 2 KMnO4. And we found out the KMnO4 number of moles earlier in this step, right? Number of moles of KMnO4 that is used up. We found it out. It was 1.2 into 10 to the power minus 3. 1.2 into 10 to the power minus 3. So KMnO4 is 1.2 into 10 to the power minus 3 millimoles. So over here itself, students, you can actually find out the number of moles of oxalic acid. So you can write 1.2 into 10 to the power minus 3 divided by 2 multiplied by 5. But we'll indicate it here as well. The moles of H2C2O4 present in 25 cubic centimeters of solution Y. Solution Y is equal to 1.2 the number of potassium permanganate moles 10 to the power minus 3 moles multiplied by 5 divided by 2. This will be 0.6 into 10 to the power minus 3 multiplied by 5 millimoles, resulting in 3 into 10 to the power minus 3 moles. Or in other words, if you want to keep it in a different format, you can write 0.003 moles. 0.003 moles. So this many moles were present in 25 cubic centimeters of solution Y. So we can write concentration of oxalic acid in solution Y is equal to number of moles divided by volume. Number of moles is going to be 0.003, or actually I prefer to write it the other way. So we will write it as 3 into 10 to the power minus 3 moles. You would all have your preferred way. Some would like to write it like this, divided by now 25 cubic centimeters. I find it easy to write 25 cubic centimeters. I find it easy to convert into decimeters cubed by multiplying by 10 to the power minus 3, right? So I can do this, right? That's why I find it easier. And then when you divide 3 by 25, the answer is going to be 0.12 moles per decimeters cube. 0.12 moles per decimeters cube. So some may find it easier, instead of writing it like this, I have seen when it comes to different approaches, you can actually write this concentration. The number of moles can be written as, instead of writing 3 into the power minus 3, some would write 3 divided by 1000, which is actually correct. And then we have to divide this by 25. We have to divide this by 25 cubic centimeters, but 25 divided by what? 25 cubic centimeters, if you want to convert it into decimeters cube, you can divide by 1000. That is what I indicate by 10 to the power minus 3. But instead of writing 25 divided by 1000, we can write 25 or 1000 over 25. again you will get to the same answer. You will get to 0.12 the same way that we have gotten over here. So different students prefer different methods. Find the method that suits you best. Find the method that you prefer and use it all the time so that you will get good at solving questions without having to use additional steps. Sometimes after getting to this point you would know the answer. Sometimes as soon as you list down or as soon as you substitute the values, you will know what the answer is without having to carry out a calculation. So students, develop a method that is easier for you and work on your calculation skills, because when it comes to a lesson like this, it will be very important to have good calculation skills. So students, that is how you would get to this type of answers without any issue. I hope you understood what we discussed here. So in today's discussions, we looked at few difficult questions or questions that are not on the surface level. Questions that require a little bit of thinking was discussed in today's session. So at home, please try your best to find more questions similar to this and attempt to solve them on your own so that you will enhance your skills when it comes to answering such questions. So that will be all for today's experiment, everyone. We spoke about the theory parts revolving around this experiment number 4, and then we moved into the lab and conducted this experiment, and eventually we went through a few very interesting questions revolving around titrations and standard solutions. Now we will be moving on from this experiment. I will meet you again in the next experiment.